Okay, good morning, everyone. I would like to welcome everyone to this World Antimicrobial Awareness Week. We are having a virtual symposium today, and this is the first session of the program. To start with, I would like to thank the organizers as well as all the other people that are involved in the process of putting together this wonderful program that we have for the week. So today, we are going to start with our Deputy Dean for the Faculty of Natural Science and Agricultural. The importance of this day. Over to you, Professor Eileen Drummond.
Thank you very much, Prof, and good morning, everybody. I would like to welcome everybody to this webinar. It's a really interesting initiative. The COVID-19 pandemic has created the urgency of controlling antimicrobial resistance, or AMR, through infection prevention and control, laboratory strengthening, surveillance, as well as antimicrobial stewardship. The World Health Organization has declared AMR as one of the top 10 global public health threats facing humanity. As such, it requires urgent multi-sectoral action in order to achieve the Sustainable Development Goals. Misuse and overuse of antimicrobials are the main drivers in the development of drug-resistant pathogens. In addition, lack of clean water and sanitation and inadequate infection prevention and control promote the spread of pathogens, which can be resistant to antimicrobial treatment. Furthermore, the clinical pipeline to develop new antimicrobials is running dry. Without effective antimicrobials, the success of modern medicine in treating infections, including during major surgery and cancer chemotherapy, would be at increased risk. Resistance to antimicrobial medicines largely arose due to the inappropriate use of such drugs in the fields of public health, animal and food production, agriculture, and aquaculture. Also, combating AMR requires a holistic and multi-sectoral approach, referred to as a One Health approach. This One Health approach, which connects people, animals, plants, and their shared environment to combat AMR, should no longer be a concept, but a code of practice. The cost of AMR is too significant to be ignored. In addition to death and disability, prolonged illness results in longer hospital stays, the need for more expensive medicines, and financial challenges for those impacted. Unless all stakeholders take action, up to 10 million people may die each year from drug-resistant infections by 2050, according to a report on antimicrobial resistance. The World Antimicrobial Awareness Week, WAAW, was endorsed at the 68th World Health Assembly in May 2015. But the focus then was antibiotics. However, the term antimicrobials, as decided in May 2020, includes antibiotics, antifungals, antiparasitic, and antiviral agents. Annually, the WHO and stakeholders aim to address increasing global awareness of antimicrobial resistance. And the theme for this year's symposium is Spread Awareness, Stop Resistance. The key objective of this movement is to improve awareness and understanding of antimicrobial resistance through effective communication, education, and training. The Northwest-University has for the past 4 years hosted very successful public and academic lectures, as well as local community engagements on antibiotic and antimicrobial awareness. This year, this message was amplified to the public by means of live radio interviews, SABC news inserts, and continued research. The microbiology subject group on the Mafeking site is at the forefront of research in combating antimicrobial resistance and creating awareness on the threat posed by these pathogens. Research conducted at the Antimicrobial Resistance and Phage Biocontrol Research Laboratory focuses on the use of bacteriophages as alternative biocontrol agents for the escape pathogens, different Escherichia serotypes, Listeria species, and Salmonella species from animals, humans, and environmental sources. Data generated from these studies indicate that both individual phages and phage cocktails have the potential to inhibit biofilm formation by bacteria species, with phage cocktails showing high efficacy. Another study reported the first occurrence of carbapenem resistance, CR, and extended spectrum beta-lactamase, ESBL, producing Enterobacteriaceae in South African beef cattle. This study made the recommendation of stringent hygiene measures to be implemented to mitigate the spread and transmission of CRE and ESBL producing pathogens in beef farms, which may be transmitted to humans via consumption of contaminated beef. Work in the Mafeking campus has resulted in collaboration and some postgraduate student exchange opportunities with laboratories in Canada, USA, United Kingdom, Australia, Italy, Poland, Indonesia, Benin, Cameroon, and a number of South African universities. So very extensive cooperation there. Research at the Potchefstroom delivery site includes the investigation, monitoring, and surveillance of the environment water bodies, wastewater treatment plants, soil, animals, and crop yields. The ESCAPE project, funded by the Water Research Commission, investigates and performs surveillance on the ESCAPE pathogens, which are known to escape clinical settings. By this project, policymakers can be informed of treatment of hospital effluent. Also, there are bilateral relations between South Africa and Norway, as well as Germany, in order to assess the spread of antimicrobial resistance genes in the environment. The Microplastics Project is generating a wealth of knowledge to inform decision makers on the spread of AMR and ARG. I sincerely appreciate you for taking time to join the warfare against AMR, a global health concern. This program contributes to the key objectives of the WAAW strategic plan in improving awareness and understanding of antimicrobial resistance through effective communication, education, and training. I would like to welcome particularly the guest speakers, as well as the staff and students of NWU. Thank you very much.
Thank you, Prof. Thank you for your presentation and the welcome address. So just some few other important announcements before we start the program. Before we continue with the program, sorry. Please make sure that you pay attention to what our speakers are saying. It's important for us for you to contribute and listen very well. So there will be question and answer section during each of the sections. So after this session, we will entertain your question. So you're also free to use the question and answer option that we have that you have on your screen. You can type your questions there. Then, in addition to that, I would also like to state that there will be many sections for this program, but this is the first session, as earlier indicated. So the next person that will present now is Professor Mulunda Mwanza, our keynote speaker for the first session. So I'll give a bit of background information about Professor Mwanza. He is the head of department for animal health and in Mafeking campus, and is also a clinician. There are many things in his CV, but briefly, he has obtained his PhD in biomedical sciences at the University of Johannesburg, South Africa. He has earned experience in toxicology, food residues, as well as mycotoxicology. So we are really glad to have him as our keynote speaker today. So over to you, Professor Molunda Mwanza. Thank you very much.
Good morning and good morning, colleagues, and good morning, everyone. And thanks for the opportunity given to me to give a talk this morning. My name is Mulunda Mwanza, and I'll be talking today about the veterinary drug residues and resistance. Today, as we celebrate, or we celebrate the antimicrobial day, and it's very important for us to also reflect on where and how these resistance antimicrobial ends up on our plates, and how do we really, what is the cause of this? And mostly, when you look at it very well, humans are exposed through their food, and among this food, we have animal products. That means your meat and all the animal products, your dairy, your cheese, which are coming on our plates, in addition to the vegetables. And when you look at both of them, they are cross-linked, and they give, the end product is that we have the same problem, which is the antimicrobial and the drug residues on our plates, and lead to problems which we are having, which I'm going to talk about in a while in my presentation. So once more, thank you to the organizers for giving me this chance. My topic today is on veterinary drugs and resistance. When we talk about veterinary drug, and we talk mostly about the drugs which are used in the veterinary medicine for the treatment of animals. And the aim of this treatment is either due to the pressure of the requests by the demand of the production. We want to produce more. That means the need of high production, the need of controlling diseases, because these diseases are coming and they affect the productivity, while we have a high demand in terms of veterinary products, meats, as well as veterinary products. As the veterinarian or animal practitioners, they require to use more products or veterinary antimicrobial, antiparasitic, and pesticide in order to protect, or in order to improve the productivity. So what are the really causes? We know that the global average annual consumption of antimicrobial is estimated up to 100 milligram per kilogram when we are treating animals in a year. And this is too much. And the process is that once the animal is injected, there should be a period of metabolizing the products, metabolizing the antimicrobial or the drug which has been injected, so that the animal can remove it from the system, can metabolize it and remove it from the system. However, due to the pressure, sometimes people do not respect those time, and they end up slaughtering animals or collecting products such as milk, which end up on the plate with the presence of this antimicrobial. It is estimated that in the next 10 years, we'll move, or there will be an increase of up to 67% of the antimicrobial which are used in animals. I just put a sketch of what is happening in terms of antimicrobial resistance. You see that the animals are exposed to antimicrobial resistance through treatments, sometimes direct to treat diseases. Indirectly, when we associate them, we add them to food or feeds to prevent diseases. And the end product is that we end in the products such as milk, eggs, meat. And these are the lead products through which the antimicrobial and drugs end up on the plate of the consumers. the most important thing also we need to know, and there is a research which is going on now, is that even through the manure which we use as fertilizer on the farms, there is a risk of transmission of this antimicrobial, because once the animal is treated with this antimicrobial, they shed them into their feces. And when we use the manure as fertilizer on the farm, even if there was no use of antibiotic or antimicrobial or drugs on the farm, these manures will transport a certain amount of antimicrobial or drug residues, and it end up in the plants. So even if someone is a vegetarian, he might be exposed to this antimicrobial and drug residues through the vegetables or the veggies or plant which we are consuming, because the manure can transport this antimicrobial and these drug residues. And the consequence is that the driver of this is mostly we have the outbreak of diseases. More and more we are having outbreak of new diseases. And
Okay, I'm not sure if it is my internet, but I think there's a bit of a challenge in hearing Professor Mwanza. So can everyone hear me? Professor Mwanza, you are muted. Okay.
the network, oh, sorry, the network. Okay, I was talking about the excessive demand of animal products and meat. The other driver of this antimicrobial residues in meat and meat products or other products is the improper dosages of these antimicrobials. During the treatments, there is dosages which we are supposed to use as veterinarian and animal practitioners. But we end up, because of the exposure of these drugs or the selling of these drugs at any shop, we have a problem with people who are not trained in terms of the use of antimicrobial or drugs. They misuse it. That means it's either they underdose the animals, and underdosing create resistance in the animal, or they overdose the animal, and that leads to the antimicrobial to end up in our plates or in the animal products and end up on the plate of consumers. There is a problem of enforcement of laws. We know that many countries, they have laws, they have regulations on drugs according to the regulations, but most of these countries, they don't follow these rules and regulations. You realize that in most of countries, they only check or test products which are exported overseas because the company importers, they have regulations and they want proper products. That's where we put more emphasis. But the products which are consumed locally by the population, there is no much regulation, or there is no much control on what is happening, on what we are consuming as local population. That is one of the weaknesses, and which lead to antimicrobial residues on plates of consumers. We have the weak financial status of farmers. That means when you are not a producer of products of antimicrobial or drugs, what happens is that there is import of drugs which are coming from other countries such as India, China, and we know that they are substandard drugs, and they are cheaper. So the farmers, they mostly go for those drugs which are not dosed properly, and when they use them, they create resistance in the animals. Remember, the resistance of an antimicrobial resistance is not only in human, it also happens in animals. That means we end up in situations where even when we treat the animal, we do not reach our target, or we do not reach the aim of the treatment. Why? Because the animal have developed resistance as well. So when farmers do not have enough financial means, they go buy cheaper medication and they use it for the treatment of animals. And this leads to all, the problem of drug residues and resistance. As I said earlier, the issue of education and expertise of farmers or in the husbandry system. That means if they are not educated, they misuse the medication. Either they underdose or overdose or repetitive treatment. Immediately there is a problem, you just treat the animal without looking on the environment. What is causing the animal to be sick? We don't look at that. And that's what we teach mostly our students, is mostly to look in the cause of the disease. Instead of rushing in using drugs, we better look on the environment and try to correct the environment, and the animal will not get sick. So there is a problem of education and expertise. And as I said, the easy accessibility of these drugs by farmers or by anyone. You can go to any shop and buy medication which are used, antibiotics. If you go in Africa, in other part of Africa, you see that even for human consumption, the antibiotics and the drugs are all over. Anyone can sell them on the market. The regulation and the law are not enforced, and that leads to the residues and resistance. So the implication is that we have the impact is on the consumers mostly, but we have also the implication on human. So we end up on the drug resistance. That means when we talk about resistance, when we use these antibiotics, when we reuse these drugs, antimicrobial, antiparasitics, that means the drugs which we use for controlling worms, internal and external worms, we see that the animal, they are no longer acting. That means the animal have created the resistance. There have been a mutation, a gene resistance which has been created. We have in human, even in animals, we have sometimes allergic and hypersensitivity reactions which occurs. This can lead up to carcinogenicity or disruption of the normal intestinal flora, where the animals now are having trouble, for example, in the digestion, where the intestinal flora does no longer function normally, okay? And we have, for example, a situation of acidosis, where we have the irritation in the animals or even in human. We have mutagenicity, that's where there is mutagenicity which occurs, or sometimes it can even lead to cancers due to teratogenicity. Okay, so globally there is, as we all know, through the Codex, that means the World Trade Organization and the Codex Alimentarius, there are maximum residue limits which are acceptable. That means these are limits which are acceptable in certain, for example, in meat and milk, for each antibiotic or for each drug. And the issue is that the application of this codex becomes a big problem for different countries. Why? Because it affects the trade. We know that many people are using these drugs and there are residues in their product. And what happens now, when they don't control or when they accept any limitation or any maximum residue limit in these products, they might not export the products. And this leads to dispute between countries. And what happens is that there is a decline in terms of exchange of products, animal products. And that affects the trades internationally. So a research has been done to see where do we have loopholes in terms of drug resistance, in terms of drug residues. Where do we have a problem in terms of the people who are acting? What is the major problem causing these drug residues? Among the professionals, when we talk about professionals, we look on the veterinarians, animal health practitioners, and the non-professional as well. We realize that the research has shown that most of the resistance, most of people who are not adhering to the are not adhering to the good practice in terms of the use of drugs and antimicrobial residues, it's mostly the non-professional, because they don't understand. As I said, the education is very important in terms of understanding how to use. However, when you look, the second group is the animal health assistants. That means the animal health practitioners. And then even the veterinarians, you find that 7% of them, there is a 7% chance that the poor practice comes also from the veterinarian. So this is something which the issue of the use of antimicrobial and drugs need to be implemented and educated, and continuous, such as these meetings are needed to inform the people, everyone, about the risk of drug residues. However, the awareness as well came as one of the most important issue for poor practices. Some people do not even know. That means that 37%, we realize that there is poor practice, which the awareness was one of the reason of poor practice. That means people were not informed that the use of these drugs might lead to a problem. Okay. And then, as I said, after administering the medication or the drugs, there is a period of waiting to allow the animal, the body, to metabolize. That means to transform and to remove the product from the bodies. Because remember, when we inject or when we administer drugs, they have a purpose, they have a target. And once they reach that target, they need to be removed from the body so that they don't end up into the in the meats or in the product. At 37%, the poor practice, at 43%, sorry, the withdrawal period is usually not respected. You see, an animal has been treated today, and tomorrow is already on the line for the milking. That is a very high risk. That means the antibiotics are going, or the drugs are going directly in the milk. That cow or that sheep or that goat should be kept away until the 21 days, depending on the type of drugs. It's 21 days, it's 2 months, or sometimes it's 15 days, or it's 7 days, depending on the manufacturer, to allow the drug to be metabolized and removed from the system. So at 43%, the poor practice or the non-application of the withdrawal period plays a very important role in terms of the presence of drugs on our plates and the poor practices. And then, as I said, the financial status of farmers plays a very important role. You can see that at 37% of chance, the poor practices is due to the cost. That means the farmer will go for a drug which is cheaper. And remember, everything which is cheaper is not the best. And when at 37% of chance, poor practices comes through the drug choice. Instead of looking on the costs, we look on the availability, and that's where comes the financial status of the farmer. As I said, the problematic of antimicrobial and resistance comes from the high demand of animal products. And the high demand of animal products leads to the increase of the use of drugs on farms. Okay, either to treat the medication, or either to prevent the disease, either to improve the productivity. And this leads to increased antimicrobial resistance. And also lead to increased drug residues, and hence it ends on the plate of the consumers. So we have different methods we use to look into or to detect the presence of this antimicrobial. We use ELISA, the HPLC, the gas chromatography, the liquid chromatography, and there are many tests which are coming up, such as inhibitor tests, and we have a lot of test kits now which are on the market. But the tests, if I can say, remains the use of the HPLC. You can see at 29%, it comes up, the HPLC is mostly used, but this requires funding, equipment, people who are trained. That means the capacity building of personnel, capacity building, and it becomes costly in terms of testing. And there is also, especially in Africa, we need what we call the invest into research and development. These equipment, these kits are very expensive because most of them are imported. And we need to develop that capacity in Africa, in our own countries, in terms of research and development, to develop these kits so that they can be available to reduce the at a cheaper cost, and they will help in terms of testing on the farm, even on the sites. The farmer can test to see if the product which is going to put on the market is good or not, is having antibiotic or drug or residues and not good for consumers. Then it can modify and change. So, as I said, we have different techniques. Some of the tests in our have been published. Some of the tests, we could see that we have the presence of, for example, sulfonamides in chicken, in beef, in pork. But most of the samples which have been analyzed here in South Africa, we did not find residues, maximum residue limit. We did not have concentration, which were above the maximum residue limit. Ciprofloxacin, streptomycin. However, tetracycline, you realize that tetracycline is one of the antibiotic which is mostly used because it's a broad spectrum antibiotic, and it's used for many diseases, especially tick-borne diseases, to treat tick-borne diseases in Africa. That's why it's one of the antibiotics which is used. I have gone into papers to see how in Africa we are doing. We will see that most of countries where we have some of the publications, tetracycline comes off as one of the antibiotic which is highly used with the beta-lactam. You see that in Kenya, in Sudan, in Tanzania, Ethiopia, Nigeria, in Ghana, South Africa, tetracycline comes as the first antibiotic which is used. So you see, even in the distribution, we see that tetracycline is one of the most used. And why? Because it's one of the strongest antibiotic we have currently. Once we lose tetracycline due to resistance, we are going to be in a catastrophic situation, because most of tick-borne diseases, most of bacterial diseases are treated with tetracycline, and it's highly used, but there is a need of information. This kind of forum are one of the forum where we need to educate our population, educate our scientists, educate our veterinarians to say we need to use it, but we need to use it with cautious. Otherwise, we are going to be in trouble in the next future. So we have, as I said, we have the challenges, which is mostly the investments. We have the issue of the metabolism, for example, of drugs. To test these drugs, it requires a lot of extraction and different methods to be used to detect them. Or sometimes we go for biomarker to detect them, to detect their presence in the body, because we cannot detect them directly, okay? Because of the, for example, the co-occurrence of these compounds can also affect the testing. The cost of analysis for that means of testing, as I said, the more there is investments, the cost becomes expensive. And the issue of diversity on products, animal products, which need to be analyzed as well. In Africa, in most of countries, the absence of legislation and control, it's a challenge, okay? There is that ethic, the challenge of ethics. That means the people who are using these drugs, or even beyond that, the people who are testing, when they find that the product is not of good quality, what is the ethic beyond that? That means, how do we stop this product from going on the consumer's shelf? So there's the problem of ethics, starting from the producer, that means the farmer, the veterinarian, up to the people who are selling. There is a big problem, and we need to look into that as well. It's one of the challenges. There is an issue of climate. We need to talk about it. Climate variability and climate change, which are occurring. We can see how hot is the temperature these days. The COP26, which has just ended in Glasgow, they are talking about the increase of temperature. What is the consequence of that in terms of diseases? That will determine also how the farmers, how the practices on the farmers, on farms. We see that new diseases are occurring on even in places where they were not occurring, because now the temperature is favorable for ticks, for bacteria to survive. And these new challenges are coming. The climate change, climate variability and climate change is one of the bigger challenges which we need to deal with to understand what is happening. And that is one of the work which we are doing in our laboratories now. We are trying to anticipate by looking the behavior of some of these bacteria, of some of these fungi. How are they going to behave with the increase of temperature? And what would be the reaction, for example, after treatment with antibiotic or drugs? So these are challenges which we need to face as a scientific community in the future. So some of the proposition which we have is to reduce the antimicrobial use in the livestock production. As I said, how do you reduce the antimicrobial use in livestock production? We need to look on the environment. However, there is a challenge, as I said, of the changes of climate, the environment. There are new bacteria, new viruses which are coming up, new diseases which are occurring. Recently, we were trying just to order eggs, fertilized eggs with one of my students, but it took us 2 months to get just few eggs. Why? Because the avian influenza has completely destroyed the poultry industry, and there is outbreaks every day. And this leads to people or farmers to use more antibiotics to prevent, and the problems continues. The enforcement of appropriate withdrawal periods of antimicrobial and drugs, and creation of awareness such as this forum. We need to expand this information and make people aware about the risk of this. As the dean has introduced, we need really to talk about this and disseminate the information as much as possible. Education of our farmers, education of all the people who are handling the drugs. Should we reduce, for example, the exposure or the accessibility of these drugs to certain people so that we reduce the issue? That is something which is debatable. It still needs debate. And the issue is that the veterinarian or the animal health technicians or the animal practitioner are not always available. And the farmer might need the medication at a certain time when he has a problem on the farm. But how does he use it? So the training of farmers, and that is what our university in this community plays a very important role in terms of training farmers in this regard as well. Promotion of disease-resistant livestock breeds, it becomes very important. The use of phages, the use of other methods in terms of treatment or treatments of animals and prevention of this bacteria. Development of rapid tests and screening methods which are cheap and accessible. As I said, we need to invest in the R&D, the research and development in Africa. We need to put more money in those, okay? I can also add, I think I didn't put it here. Can we need to go back to our indigenous knowledge to try and see which products we can use in terms of treating our animals. How were our ancestors treating their animals in that time? We can look on what was good, what are the products. We still have some new compounds which we can
sorry to interrupt you, Professor Mwanza. If you can just please wrap up. Your time is.
It was my last slides, and I would like to thank the organizers, and I would like to thank everyone for listening to me. Thank you very much.
Yes, thank you very much for that wonderful presentation, Professor Mwanza. We appreciate that. If there are questions, we will have to take the questions at the end of the session. So please hang around. Well, once again, thank you for your presentation. So we will now move to the second part of this session, where we will have the students' presentations. And the first on my list will be Mr. Tuto Mahome. Tuto, are you ready?
Hi, Paul. Yes, I am ready.
Please go for it.
Okay. Good morning, everyone. My name is Tuto Mahome, and I'll be presenting on my master's dissertation title. I was working on with the title Microplastics Pollution and Associated Microbial Community Harboring MC beta-lactamase genes in a South African river system. Plastics are widely used across industries because of their long-term durability and also low-cost efficiency. And despite the beneficial use of plastics, it has been established that they have become quite a concerning pollutant, more especially in marine settings. Now, it is estimated in South Africa that about 15,000 and between 15,000 and 40,000 tons of microplastics is carried to the ocean. With that being said, microplastics are particles with a diameter less than 5 millimeters and greater than 1 micrometer. And they are classified into two groups. We have primary microplastics. These are substrated and manufactured to be microscopic, and you usually find them in your hand cleaners, your shower gels, and your face scrubs. And then whereas secondary microplastics are microplastics that originate from larger fragments, from larger pieces of plastics, and as they go through the environment, they undergo tearing and breakage, and when we isolate them, then they are less than 5 millimeters and they fall under the classification of microplastics. Over the years, we know that our rivers and our river systems and wastewater treatment plants have been reported to be reservoirs of bacterial pathogens and also antibiotic-resistant genes, as they do not optimally eradicate these agents. With that being said, in terms of microplastics, our wastewater treatment plants are not designed to remove microplastics. They can remove the macroplastics, but what we've seen is that they can still release a substantial amount of microplastics. It has been reported that treatment plants remove up between 83 to 97% of microplastics. And the growing concern from a microbiological point of view is that microplastics can be colonized by bacterial cells, and they can maintain their stability on these plastics by forming biofilms. And this is usually termed the plastisphere. And there are some studies that have reported on the presence of microbial life on microplastics. And also just in 2018, there was a study that reported that microplastics, within the plastisphere, there is an exchange of genetic material between microbial cells and the surrounding water community. Following that, I embarked on a study where I did both lab and environmental comparisons, and I collected water samples for the first part of the microcosms. I collected water samples from the Moy River, where I took fresh water without impact of the wastewater treatment effluent, and I took water also from wastewater treatment effluent. And I incubated microplastics, which were bought from an industrial manufacturer. And they were first sterilized and introduced into these mediums for a period of 14 days, and were analyzed to look at the surface and microbial colonization process over time. With that, also for the environmental part of the experiment, I went and filtered river water on site, where I found 206 microplastic particles for analysis from filtering 1,800 liters of water. And from the environment, what we saw was that fibers were the most dominant microplastics that were found, and they were followed by fragments, and then foams, which are usually your polystyrene type of plastic, and then also between the shared majority was the microbeads and films. Now, following that, we looked at the surface properties using scanning electron microscopy, and with time we saw that from the plastics that were introduced with no microbial cells, colonization began to take place, and that in nutrient-rich settings, that is your wastewater treatment effluent, this colonization by microbial cells on the plastics were rapid, and they formed biofilms quicker than in freshwater settings, however. And then in the river water, basically, it was a delayed process. Whereas when I went also to look at the environmental samples, we found that because we cannot track when the microplastics was introduced into the water, we find that were heavily colonized by bacterial biofilms, different microbial cells, and eukaryotic organisms. And the thing was to do a 16S metabarcoding, and what we found is that the bacterial community composition on microplastics was less rich, less diverse, and less even than in the surrounding water. And also that we included wood as a substrate to check as a control substrate for a non-plastic control, to observe whether there's going to be any difference. And of course, still microplastics contain less of that. And also when we look at the environment section of it, we also found similar results where the bacterial diversity was less rich and less dominant than in the surrounding water. Following that was to do biomarker analysis, whereas we found that there is some selective enrichment whereby some bacterial families were more dominant on certain substrates, and for example, Alcremonidaceae family and
so just a reminder that you have a minute to go. Sorry to interrupt you. You have a minute to go.
Okay, so okay. I was counting. I think I have 3 minutes, but it's fine. I'll just wrap up quickly. And following that, we see that the selective enrichment of microorganisms on different plastic types. Following that was to determine the prevalence of antibiotic-resistant genes on these biofilms found on microplastics, and we saw that in the in microcosms there was more antibiotic-resistant gene copies that were found on microplastics than in river water and wood substrates. And then whereas in the environment, from the river part, it was more genes found on microplastics than in water, and it was quite the opposite for wastewater treatment effluent, where is obviously it's more richer than the smaller substrate. Following that was to do prevalence of the MC beta-lactamase genes, whereby we saw that some gene groups were more the gene copies were more on microplastics than in the surrounding water samples, which means that there is a proliferation of these genes in the plastisphere, and also how we see that in wastewater treatment plant water effluent, it was more gene copies that were found. And what we also found is that these genes where the diversity of these genes were more, especially in high abundant areas where there's more people. And this is the site, just to show the site area where I found more of these genes and high gene copy numbers. Also, this correspond with what Dr. Cotier had found, that with more, where there is higher population densities, there is more gene groups that you find, and also where there is less gene copies, as from site 1. With that being said, my study served as a pilot study for investigating microplastics and microorganisms and the potential role of microplastics in antibiotic resistance dispersal. And I came to the conclusion that the abundant colonization, selective enrichment, and potential selection of potential pathogens on microbial groups, and related with that with the high gene copy numbers, may suggest microplastics as vectors for antibiotic resistance and bacterial pathogens, and they may also transfer between microorganisms where non-pathogenic and non-pathogenic organisms. With this said, I'd like to acknowledge the following people who have assisted me with the study. Thank you.
Thank you, Tutu. We've been doing very important work on microplastics, and we appreciate your talk. So there may be questions for you, Tutu. So say again. No, so there may be questions for you at the end of this session. So please hang around to answer any questions that may be directed to you. So our next speaker will be Jaco Mohle. Is also from the Unit for Environmental Sciences and Management. He's going to be talking about the construction and validation of an ARG plasmid DNA library for environmental analysis. Jaco, over to you.
Thank you so much, Prof. Rashid. All right. For my World Antibiotic Awareness Week presentation, I will be presenting my project entitled The Construction and Validation of a ARG Plasmid Library for Environmental Analysis. All right. So, as you all know, antimicrobial resistance is one of the most serious global health.
Sorry, Jaco. Sorry.
Yes?
I assume you are not alone in the room where you are talking, right? Where you are using the mask.
Must I take the mask off?
I just assume that if you are not alone, then you have to use your mask. I just assume that your voice will be clearer without a mask.
My apologies. People were in and out of the lab, but the door is locked now. Sorry, force of habit.
Okay.
Anyway, microbial resistance is one of the serious public health concerns and also economic. In 2015, the World Health Organization started the Global Antimicrobial Resistance and Use Surveillance System, from which South Africa adopted the AMR National Strategy Framework. However, the AMR stewardship programs, especially in primary healthcare facilities, is not really implemented, if not scarcely. And also surveillance, management, and prevention systems are nearly non-existent. So the only data we have, according to this, one of the best and most detailed is that of the ARM surveillance report from South Africa from the National Department of Health. However, in 2018, the General Household Survey released data that 47 million South Africans did not have access to public health care, meaning public health facilities are well, its resources are scarce as they are, so they cannot keep up, which is a very big problem. So the responsibility to analyze the situation or collect data falls onto us researchers. So when we talk about antimicrobials, it's usually antibiotics, antivirals, antifungals, and antiparasitic. But for the purposes of my project, I will be focusing on antibiotic resistance. Now, antibiotic resistant bacteria, all of them carry the antibiotic resistance genes. But there are few of them that are quite dangerous to us, which we need to focus on specifically, and that is of the escape organisms, especially, and some others, as Shigella and Clostridium. As these antibiotic-resistant bacteria carry their genes, they become environmental contaminants, and these environmental contaminants disseminate through aquatic environments. And as some of you might know, low-tech aquatic systems act as reservoirs for antibiotic resistance. And the lack of surveillance systems put in place emphasizes the necessity to determine the prevalence and their abundance in these systems, as they are regularly shared between environmental and anthropogenic settings. So just an example here, this was a study done in the Yangtze River in China. There are in a total of 6,300 kilometers. From the start till site 9, before the river reaches the estuary, some of the antibiotic resistance genes doubled in abundance, while others increased tenfold, which is a serious concern. Now, as the river water is mainly used for drinking water, irrigation, agriculture, they disseminate to the anthropogenic settings, and then the majority of them will return to aquatic systems. This can have large ecological impacts, especially as bacteria are able to transfer their genes via horizontal genes transfer, and then pass that gene on to their daughter cells through vertical gene transfer. So, however, studies like this is usually time consuming and expensive, especially if you're using next generation sequencing. Moreover, the study I used as an example also took in seasonal changes into account. So my project is on the construction of ARG plasmid libraries as an analytical aid to help streamline the research process. So I have a few aims and objectives. My aim is only to construct a library from partial resistance genes and to standardize these genes for quantification of genes in the environmental samples. So just a few objectives I have in order to complete this project. I have to isolate genes by means of PCR, followed by Sanger sequencing just to verify that they are the correct genes. Assemble a plasmid library using the amplified genes to standardize quantitative polymerase chain reaction protocols for comparative analysis by utilizing the plasmid libraries as positive controls. And then finally, to conduct a comparative statistical analysis between sample locations to identify emerging patterns of interest. Now, just an overview of my experimental design. In the beginning, I extracted eDNA from influence samples because, of course, that's where the majority of them will lie, and amplified them and analyzed them through agarose gel electrophoresis. As you can see on the right side, they have been sequenced with Sanger sequencing and then characterized by the BLASTIN application from the comprehensive antibiotic resistance database, or CARD. Following that is the actual library construction, in which the inserts were ligated into my vectors. Then I did my electroporation, bacterial transformation. They were incubated, the plasmids were extracted, and then finally, the fun part is just to standardize the qPCR. So they were amplified. I used my standard curves to calculate the quantities. And so what I end up with is a known quantity of copy numbers. So once the library is constructed, here's where the actual investigation begins. Is now that the library is constructed, I can use them as positive controls and they're standardized. So my sampling will be taking place upstream from the Potchefstroom wastewater treatment plant, and it will end where the Moiravier ends or meets the Vaal River. From there, it's DNA extraction, PCR assays, and then the quantification of the ARGs using standardized qPCR. For my statistical analysis, data normality will be completed via the Shapiro-Wilks test. Difference in gene copies will be completed with the Mann-Whitney U-test, and the prevalence values will be completed with the Kruskal-Willis H-test, followed by Dunn's multiple comparisons or post-hoc test. So in conclusion, after completion of the study, the environmental analysis, for environmental analysis, the constructed ARG libraries can be used can serve as positive controls during PCR assays, serve as standard for qPCR during quantification of ARG copy numbers, investigate the prevalence and abundance.
So Jaco, thank you very much, Jaco. You need to round up now. I give you 30 seconds to do that, please.
Okay, in a specific location, investigate trends in ARG dissemination and identify emerging patterns of interest, and then identify ARG hotspots and provide insight regarding aquatic ecosystem health. Downstream applications of the ARG library will significantly streamline future ARG research. It can be used in phylogenetic studies. It'll be more cost effective because everything has been completed beforehand. So we can just go out and do the analysis. And it will also aid in ARM, antimicrobial resistance surveillance programs. Thank you.
Thank you very much, Jaco, for the presentation. I can see that you've done a lot of work, and that's very commendable. Please hang around. There may be questions for you at the end of the session. We'll take questions for your presentation at the end of the session. So we will quickly, because we are running out of time now, so we'll quickly move to the last presenter for this session, the keynote address 2. This is going to be presented by Dr. Agbankwe. He is actually from a university in Benin, University of Abomi Calavi in Benin. I hope many of us will know where Benin is. Benin Republic is a country in the West African. It's a West African country. So Dr. Agbankwe is going to be presenting on a topic title. He's going to be presenting for us on combating antimicrobial resistance in Benin Republic, importance of surveillance, and some approaches to search for potential solutions. I'm sure we would also enjoy his presentation. Professor Agbankwe, are you ready?
Yeah.
Over to you.
Thank you. Okay, hi everyone. Before they start, want to thank the organizer for this section. my presentation talking about combating antimicrobial resistance in Benin Republic, importance of surveillance, and some approach to search for potential solution. So please let me switch off my video to avoid the connection issue. Thank you. Okay. So one of the greatest threats to humanity in the 21st century is the circulation of antimicrobial resistance microorganisms and the global spread of antibiotic resistant genes. Let me give you a brief reminder. Antimicrobial resistance exists everywhere and can impact anyone of any age in any country of the world. So what is antimicrobial resistance? Is the development of resistance in microorganisms to an antimicrobial medicine to which was previously sensitive. As the result, the antimicrobials used to treat infections are no longer effective, limiting the treatment option available and therefore making the most common infections more difficult to treat. Internationally, this is growing concern over antimicrobial resistance, which is currently estimated to account for more than 700,000 deaths per year worldwide. Antimicrobial resistance is a problem that concerns every country, irrespective of its level of income and development, as resistance pathogens do not respect borders. Antimicrobial resistance is a serious global health threat and is predicted to cause significant health and economic impacts, particularly in low and middle income countries like Benin Republic. In May 2015, the 68th World Health Assembly adopted the Global Action Plan on Antimicrobial Resistance, which reflects the global consensus that antimicrobial resistance poses a profound threat to human health. So antimicrobial resistance surveillance is the cornerstone for assessing the burden of antimicrobial resistance and for providing the necessary information for action in support of local, national, and global strategies. In Benin, as in many developing countries, the threat of antimicrobial resistance is increasing at an alarming rate and with notorious severity due to gross misuse of antimicrobials. It is well known that any use of antimicrobials, no matter how appropriate and justified, contribute to the development of resistance, but widespread, unnecessary, and excessive use makes the situation worse. Non-compliance in the use of antimicrobial was many repercussions upon resistance, and poverty is a major root factor of antimicrobial misuse in developing countries. To better appreciate the cause of antimicrobial resistance, we need to understand the various sequential steps involved for a drug to get to a patient and the eventual use, which includes production, distribution, prescription, dispensing, and finally consumption of the drug by the patient or use in animal production. Consequently, any imprudent practice along this flow may result in the emergence of resistance. So for the efficiency of sustainable fight against antimicrobial resistance, it will be necessary to control the different steps of the antimicrobial resistance or drug flow. As in Benin, the pharmaceutical industry is still at the embryonic stage. The Beninese government have focused for the last 4 years on the last 4 stages. Like I said, distribution, prescription, dispensing, and consumption. So what about the distribution? For a better traceability of the distribution of drugs and to avoid the sale of counterfeits, adulterated, and poor quality antibiotics, one of only of state company has been created for the distribution of drugs, especially antibiotics, to wholesaler and semi-wholesalers. Thus, the sale of drugs in the streets and in market is prohibited and repressed. In order to ensure the quality of medicine and antimicrobial in particular, a reference laboratory for quality control is currently being built. Drug sellers usually have little or no knowledge of the required dose, regimen, indication, or contraindication. Thus, for the past 4 years, only pharmacists, veterinarians, and licensed physicians are authorized to write a prescription. Drug and antimicrobial can only be purchased in pharmacy, health centers, and veterinary practice. So all the 3 steps previously represent lead of the 4th step, the consumption of drug or antimicrobial particularly. This allows to avoid high rate of self-medication and lack of treatment compliance. All these efforts have been supported in regular through Benin's national antimicrobial resistance plan and lawyers. The surveillance of antimicrobial resistance is based on the result of antibiogram routinely performed in the laboratory of biomedical analysis in public hospitals. The data shows on 2016 rates of 58.5% and 88.2% resistance of amoxicillin plus clavulanic acid by E. coli and Klebsiella pneumoniae, respectively. Rate of over 50% were also found for these genes with respect to ceftriaxone, gentamine, and ciprofloxacin. A resistance rate of 52.5% was reported for Staphylococcus aureus strains, again, methicillin. So in the animal health sector, the situation is even more complicated because as Benin has only 2 public veterinary laboratories. Therefore, there is a lack of data on antimicrobial resistance in animal health. The same is true in the environment sector. Therefore, the results of academic research are filling the gap to improve antimicrobial resistance surveillance in Benin. But this surveillance must continue for an update of the policy of management and use of antimicrobial and to fight effectively against antimicrobial resistance. So we know that the combating of antimicrobial resistance is not the business of a lone country, so it's the business of the all African countries. So that's why we need the collaboration with academic institution or research institution to do the deeping research about antimicrobial resistance. So, but as scientists, we must look for alternative solutions to the use of antibiotic leading to a great, effective, and sustainable reduction of the impact of antimicrobial resistance on human and animal health. One of the promising avenues of this alternative solution is the use of bacteriophage for integrated control of multi-drug resistance bacteria through phage therapy or biocontrol by phages. What about the phage therapy opportunities? Phage therapy is the most credible option for dealing with the post-antibiotic area. Several success stories have been demonstrated in both humans and animals in the fight against infectious bacterial disease. Opportunities to pin the routine use of antibiotics in farms and in farm animals in order to have products without chemical compounds. Absence of drug residues in food animal, in tissues, possibility of proposing a period of withdrawal of antibiotic, possibility of marketing phages. The production of phages is very simple economically with biodegradable waste without impact of the environment because phages are specific to each host, hence the ecotoxicity on the potential host of phage. So what about therapeutic use phages are used in humans for the treatment of infection. Preclinical data are available. Use of phages in combination with other antimicrobial and about the use in livestock, management of production disease and productivity improvement. Also management of zoonotic disease and food safety. So let me present you the phage therapeutic challenge. As the challenge, there is a lack of knowledge about the role of phages in gene transfer mechanism and the acceptance of the things.
My apologies, Dr. Bakri.
Yeah, this is my last slide.
Okay, that's fine. You still have like 3 minutes more, it's fine.
Okay. So the limited knowledge of phage kinetic in situ and in vivo regulatory issue, safety, gram-negative endotoxicity issue, lack of regulatory framework, and clear procedures for clinic trials. About the commercialization, we have the potential, profitability, weakness to investments to and consumer perceptions about the presence of virus on food. So thank you for your attention. Thanks.
Thank you very much, Professor Bakri. We really appreciate your ability to present the wonderful work you've been doing to us. Before we go in the answer and question session, I would just like to offer a quick apology to all the participants, especially the fact that we experienced some glitches that are related to load shedding problem here in South Africa. We see that some of the panelists were in and out of the meeting, which is related to the fact that the lights or the electricity in both my Kent campus and Potchefstroom campus were taken by ESCOM. So please, we apologize for that. And it also influenced the way we communicated even prior to the beginning of this meeting. So our apologies about that. So now we move into the question and answer section. And I cannot actually see any question here that anyone has posted, but please raise up your hand to ask your questions, and I would give you the opportunity to ask your questions. It can be for any of the presenters that we've had today. Luckily, we've had two keynote speakers for this session, as well as 2 student speakers. So if you have any question for any of them, please raise up your hand. I can see Professor Collins Ateba, who is raising up his hand now. Probably you can open the floor. Thank you.
Okay, thank you, Program Chair. I have a question for Prof. Mwanza. I mean, it's just something that I thought I wanted to discuss here. I don't know if Prof. Mwanza is there, if he's not in another meeting. Prof. Mwanza, are you there? Okay, I think maybe it's something I can discuss with him in person so that we don't waste time here. But for me, just to share with the colleagues, I mean, they are in an animal health facility where they run both a small and large animal clinic, and they provide service to the community. And my something that I've loved to find out from him is we all know the contribution of animals, especially those that are sick, that visit veterinary facilities, the contribution they might play in the development and also spread of antimicrobial resistance, both the genes as well as the pathogens in the environment. So I wanted to find out from him any strategies that they put in place so that they do not, I mean, one would say we don't want to misuse antibiotics, but what are the strategies that they have in place such that they are not seen as one of those who are, using antibiotics on animals? He made mention of proper diagnosis before treatment. Is that what is happening? I mean, that's something that I really wanted to find out from him. Thanks.
Thank you, Professor Ateba. Unfortunately, Professor Mwanza is not available to answer your question, but the fact that he's a colleague, I think this is something that you can ask him in person. So any other question that we may have? Okay, questions before we close this section. Are we also, okay, let me just go into one of the student presentations. Miyako, you presented something on real-time PCR for your work. Yako, are you there?
Hello, Prof. Yes, I'm here.
No, I just wanted to find out. Hello, I'm here also. We had a problem with, I could not. We had a problem with electricity this side. Yeah.
So, oh, okay. Who is talking now?
Prof. Mwanza.
Oh, Prof. Mwanza, you are here now. Welcome back.
Yes.
So, okay, did you hear Prof. Ateba when he was asking his question?
No. We had a problem with the connection was not.
Yeah. Oh, okay. I thought you are okay, Prof. Ateba.
Okay, Prof.
Just quickly ask that question so that
just to summarize,
we are running out of time.
Just that the facility. I mean, thank you for presenting, but the animal health facility, we know they have both small and large animal clinic, and they serve the community. And you have animals that come in and they undergo treatment. So I wanted to find out what strategies are in place to ensure that this process is not seen as one that results or also contributes, if I may say, to the development and spread of multi-drug resistant strains.
Okay, as I said, we cannot localize it to the Department of Animal Health here. We as a training institution and training our students, we try as much as possible to train them on the good and best practice in terms of antimicrobial and drug use. That is what we train our students. That means they have to know the dosage, respect of the withdrawal period, and minimum use of antibiotic as much as possible. Well, that is what we train as students. But this is a global issue, and this kind of meetings are very important. That, as I showed in my slide, up to 37% is a problem. It's a problem of awareness. That means many people are handling drugs and not aware of what they're supposed to do and how they're supposed to use them. And then many, not only that, and even sometimes people who are knowledgeable are misusing the drugs. So we need more awareness and information session such as this, and then pamphlet and distribute them as much as possible. That's what we need. Probably even at the point where they're selling drugs, this kind of information should be there, summarized into pamphlet, and they inform the population need to be informed about this. Thank you. Hello?
Yeah, thank you for the answer to that question. We appreciate. So I would take one more question. Is there anyone who wants to ask another question? One more question. Is there anyone who wants to ask another question? So if there is none, I can also ask Yako the question I wanted to ask the other time. Yako, are you still there? Yako Mula, are you still there? You are muted, I guess.
Yako is not on the panelist list anymore. I think he's
It's not
disconnected.
there anymore.
Internet.
Oh, internet problem. Okay, colleagues and all the participants, I think we've had a good session. We thank you for your participation in this session. The next session will start in another 10 minutes, so we have a break now. So you can prepare for that session. And I hope you would also enjoy the next session. The next session will be hosted by Dr. Lekota. Thank you very much once again, and keep well. Bye.
Good morning once more again. Welcome to the second session. I'll be chairing this session. I hope everybody's back and we are good to go to the second session. So welcome once more again. In this second session, we've got 6 speakers in this session, and our first speakers will be it will be Prof. Vincent Mnamdinga Chigwa. So just a little bit background of Mnamdinga. He completed his PhD at the at the University of Fort Hare, and now he is at the University of Nigeria in Nsugbe, and he is involved in numerous projects, and he's affiliated in the coordinator, Water and Public Health Research Group, the Department of Microbiology, Faculty of Biological Science at the University of Nigeria, Nsugbe. So over to you, Prof. Vincent.
Prof. Vincent, you will start your presentation. We're just having some technical difficulties on the program director side. So when you are ready, you may start and share your screen with us. Thank you.
Are you able to share your screen, Prof. Vincent?
Okay, thank you. Thank you.
Okay.
Can you see my screen now?
Yes, well clear. You can just as your PowerPoint presentation, put it in a presentation mode. For those who are not presenting, kindly make sure that your mic is mute. Please make sure your
Thank you, moderator. I believe you can see my slides now.
Yes, you can go on.
Thank you. I'm speaking on antimicrobial resistance strength in Africa, the role that freshwater bodies are playing in this increasing challenge. Thank you. Like you mentioned, I tell us a little about myself. I did my PhD in Fort Hare and joined the University of Nigeria in 2006. And currently I did the Water and Public Health Research Group. And our group is quite a multidisciplinary one, in interfaculty. And so we have diverse research teams that through aquatic environments and human health, through water resource management and governance, and down to bioenergy and biochemicals from wastewater. Sorry, we've had some funding and support and collaborations, and our group also has been productive. Now to antimicrobial resistance threat in Africa. Why are we interested in freshwater? to me, really, when we are talking about water, there are usually two questions to ask. Is the water available? And if water is available, what's the quality of water in question? And I want to say that water is available to us as fresh water comprising groundwater and surface water. And by definition, fresh water is water containing less than 1,000 milligrams per liter of dissolved salt. Having said that, there is the total volume of water on Earth is about 1.4 billion cubic kilometers. That's huge, that's huge. But then if you look at that, you will see that about 97% of that is salt water. So we are left with 3% that is fresh water. And this 3% again is actually locked up in ice caps and glaciers. That takes over 68% of that. And then we have groundwater, if you have the mechanism to access it. And of course, the surface water that are available to us. So you put this together, you discover that yes, there is water everywhere, but very little water available. And even that which is available, you must still ask the question, what's the quality? Is it fit for use? Or is this water going to be a problem? We just want to point out more that when we speak of surface waters, they include all the lakes and reservoirs. That's man-made gatherings of waters and the streams and canals that are often keep flowing with water in our major cities. And of course, the swamps and freshwater wetlands. So coming to antimicrobial resistance is, you see, this occurs when microorganisms become resistant because the agents through which they could have been eliminated, they have become resistant to them. And so through mechanisms such as mutation or genetic exchange. Resistance can occur. Resistance in these microorganisms can occur either in humans or in animals, and actually also in the environmental settings where the release of human animal excreta or the presence of antimicrobial agents and other pollutants. For instance, we have antimicrobials that are released from pharmaceutical industries and unused ones and hospital waste and all that. They get into the environment, and all of that, including in the presence of other pollutants, would actually favor the persistence of resistant strains. So we want to say in this presentation that basically water can play the role in the spread of antimicrobial resistance by three main ways. Number one, that water could result in dispersal, and the spread of resistant pathogens. And this will result in transmission of waterborne diseases. And when waterborne pathogens are transmitted, that means that there will be need to treat man and animals. If they are transmitted to plants, they will still find themselves eating and cause problem in man, requiring treatments again with antibiotics. Of course, there is this scenario of silent transmission where resistant microorganisms with low pathogenicity, not really, some of them are quite even part of the normal flora like Escherichia coli. And they can acquire resistant genes, and this will cause problem when the person become vulnerable or immunocompromised individuals. They will cause infections. And they can as well transfer, you can imagine a horizontal gene transfer in the human gut, the number of bacterial organisms that are in the gut, and if somebody had acquired, E. coli had acquired pathogen-resistant determinants, resistant genes from pathogens, and then transfers it to another organism that comes in contact. That will present huge problem. Thirdly, the release of fecal matter and other pollutants, including antimicrobial compounds, like I've mentioned, from fabric industries, or they are just decided because they are not used, into the environment, will basically do what? They will promote resistance by creating conditions that will favor actually those organisms that are resistant. They will flourish while the antimicrobials are eliminating the other organisms that would have been competing for them. And these ones will transfer their resistant genes. And what's the situation we have here in South Africa with relation in sub-Saharan Africa, in relation to hygiene issues and water contamination by fecal matter. In 2015, it was estimated that about 663 million people worldwide still use unimproved drinking water sources, including unprotected wells and springs and surface water. Now, I'm interested in this because nearly half of all people using unimproved sources live in sub-Saharan Africa. And not much has improved. By the end of 2020, only 54% of people in sub-Saharan Africa use safe drinking water. And the current practice for water and wastewater treatment in Africa is hugely insufficient to ensure safe water and basic sanitation. If we don't have safe water and sanitation is a challenge, the resultant effect is that we keep having rivers and dams and lakes and shallow wells that are contaminated. Yet they are our major sources of water, both for drinking and other purposes, for irrigation farming, for vegetable production. And all of this will compound the problem and keep contributing to the spread of antimicrobial resistance. Now, fecal contamination will introduce microorganisms as well as organic matter. We know that the pathogenic bacterial sources, it truly presents a serious aquatic environment. The genetic materials can be shared between bacteria under selective pressure. And actually the pressure can be increased knowing that there are other pollutants in the environment. We'll have a situation where now the antimicrobial resistant genes would move across environmental bacteria and pathogens. Now, the situation we have here is being in sub-Saharan Africa is being encouraged by a lack of an antimicrobial surveillance system. I know that a few are happening in some areas like in South Africa, but largely so antimicrobial surveillance is lacking in sub-Saharan Africa. And now there is open defecation is another issue. As people do open defecation, fecal matter will always find its way back into the water sources. And it may surprise you, we have very, very insufficient infrastructure. There's a huge lack of wastewater treatment plants in places like South Africa, there are a lot of wastewater treatment plants. But as huge as Nigeria is, over 210 million people in population, we have just 4 wastewater treatment plants, 4 standard municipal wastewater treatment plants. The result is that people depend on pit latrines, people depend on septic tanks, and all of this will end up contaminating the underlying groundwater. And in cases where there is flood, still surface water will be contaminated by the treatment systems. Again, we want to point out that there is a practice. I don't know how much is obtainable in other areas, but here where I am in Nigeria, there is this practice. Because there is no place for treatment of sewage, people actually will abstract sewage from households and dump them directly into wastewater. This video clip, you could see a woman fetching water. It is the same water source that this lady has had to fetch water for domestic use, into which this tanker is dumping sewage. That's what is obtainable, and all of this will help. Now, I just want to come closer to what we have in Nigeria. Imagine a country where cattle feces contaminate surface water because cattle is reared free range and hard watering is done in situ. Imagine a country where untreated sewage is dumped into a river, as we've already shown by Clay. I've mentioned that we have only 4 municipal wastewater treatment plants. And when we are saying municipal, 3 of these are actually located in the universities, so they don't serve the entire city. Imagine also that untreated sewage, untreated surface water and groundwater are used for fresh produce irrigation. These are transmission channels that will get pathogens and antibiotic-resistant bacteria into the human system. Imagine also that the highest number of people practicing open defecation dwell in Nigeria. 14 out of the 744 local governments in Nigeria, only 14 are open defecation free. Then imagine a country where virtually all antibiotics are available for over-the-counter purchase. The resultant effect is that there's a high level of abuse and misuse of antibiotics without prescription. Yet, the over 210 million people are doctors. They prescribe for themselves, and they just go there and they buy antibiotics and use. Imagine also that there is a lot of substandard antimicrobial products in the market for people to purchase. The result, all of these are contributing to the continued emergence, increasing cases of antimicrobial resistant infections. Okay, this table shows actually, I had done this to highlight the huge disparity. South Africa, just a little above 60 million in population, has 963 municipal wastewater treatment plants. Nigeria is over 210 million in population, and we have only 4. The case is better compared to Ghana, where there are 44, and in Kenya, there are 49 wastewater treatment plants. Again, I need to highlight that even when we have this, even in South Africa where they have this number, it is not all of them that are functioning well. A lot of them in Kenya, they are reporting that it's just about 20% of what they have that is effective. Again, this table number 2 is showing some selected studies that have been done in which the works have detected, like in Lafite et al. In 2020 worked on a river in Kinshasa, DR Congo, and they detected beta-lactam resistant genes, carbapenem resistance, and you could see all of that, Oxa, and the rest. But some people have worked in shallow wells in Uganda. And screen for, hello? Hello? Hello, can you hear me? I appear to be having network challenge. Can you hear me?
Yes, we can hear you.
Okay, thank you. A lot of work has been done. We've just shown some selected ones, but there are still a lot of challenges, and there's some poor level of funding for research, and there's lack of equipment. We discover in most of these studies, either the person who is working in sub-Saharan Africa is linked to, well, basically what studies are done linked to South Africa, also Europe and the US. And there's a huge lack of institutional support. When people are preparing grants that will enable them to get grants and do research that will help produce data that will guide policy, how wonderful it will be that these data are available, and then we are struggling with whether government is interested in implementation or putting them to use. But these data really are nowhere. You will Google, in our search, almost every surface water in South Africa is captured online. All the wastewater treatment plants are captured. You can't find that for Nigeria. You can't find that for Ghana. You can't find that for Senegal.
Sorry, Prof, you're gonna have to wrap up. You're left with a minute to wrap up your presentation.
Thank you. We need to deal with these challenges, and through establishment of collaborations, which this symposium is giving us opportunity to, within Africa. There is need actually that institutions in South Africa that are funded would proactively engage other institutions in Sub-Saharan Africa in collaborative research. There's some degree of, and for the future directions of research, we need to really begin to look at how to advance water hygiene and sanitation in Sub-Saharan Africa. There is a lot of that in the area of shallow wells. How are these antimicrobial resistant bacteria and resistant genes, how are they moving? How at the end do they get back into the human system where they can cause harm? Again, I've been wondering, we have standards for bacterial counts in water quality. What about nucleic acid? Since we know that DNA is long lasting and could actually get transferred through transformation, or basically by conjugation. And again, we need to begin to ask how organic matter in sewage, do they favor horizontal gene transfer? How the organic matter in sewage? Under water treatment environment, would there be increased transfer? We need to do a lot of research. And I really want to say that, end this with some Coleridge verse that says, water everywhere, not a drop to drink. A water-focused approach are key for detecting the spread in populations and preventing antimicrobial resistance spread to everywhere. I say thank you very much. Nkosi Kaku Dalonorine. Thank you.
Thank you so much. Thank you so much, Prof, for such wonderful insight information. That was a nice presentation. I see there's a lot of much gap that still needs to be done in terms of horizontal gene transfer, depending on what organic material that is in there. Quite interesting field to be also focusing on. So our next presenter is Dr. Emilia Njema Lyonga. She completed her PhD in 2017 at the University of Yaoundé, one in Cameroon, in the Faculty of Medicine and Biomedical Sciences. She holds also a master's in public health, where she completed at the same university. She's now currently a senior lecturer and a research under the Center for the Study and Control of Communicable Disease in the Faculty of Medicine and Biomedical Sciences at the same university. Over to you, Dr. Emilia. Emilia, are you here?
Yes, I'm here.
Okay.
Network is a bit slow. Thank you very much. Can you hear me?
Yes, we can. You can proceed.
Okay, thank you very much for presenting me. I would like to present myself again. I'm Emilia Lyonga. I'm a senior lecturer from the Faculty of Medicine and Biomedical Sciences, University of Yaoundé 1. So, I would like to thank the dean, the vice dean, the directors, the head of department, first of all, for receiving me in the faculty for my research exchange, and secondly, for selecting me to carry out this presentation on a virtual symposium. The work we're presenting is entitled Genotypic Diversity and Characterization of Quinolone-Resistant Determinant from Enterobacteriaceae in Yaoundé, Cameroon. It has been published in an open journal of medical microbiology since 2020, and here are the authors. This is the abstract. We will follow this plan to carry out our presentation. One of the reasons that caused us to carry out this study is the fact that Enterobacteriaceae account for over 80% of clinically significant isolate of gram-negative bacilli in most laboratories. And they are implicated in many types of infections, including abscesses, pneumonia, meningitis, septicemia, intestinal infection, urinary tract infection, wound infection, and many others. And most frequently, they are treated with fluoroquinolones, which is the drug of choice. And these fluoroquinolones account for about 11% of overall prescription of antimicrobial in medicine worldwide. So this class of antibiotic is bactericidal. It kills the bacteria actively and acts mostly on the topoisomerase 4 enzymes, or it acts mostly on the topoisomerase 4 enzyme or the bacteria DNA gyrase. And these enzymes are important for proliferation and cell growth of the bacteria, and thereby inhibits DNA transcription and replication of the bacteria, leading to death. The first detected quinolone-resistant gene was the KONR, and it was detected in Alabama, USA, in an E. coli bacteria. These genes have been identified in many members of the Enterobacteriaceae family since its first identification. They are found on the plasmid, and so they can easily be transferred from one species to another species and within the same species. And it is believed that the KONRA gene originated from the Swanella algae, an environmental species from marine and freshwater. After the initial discovery in Alabama, the QNR gene have been detected worldwide, in Ghana, in Nigeria, but unfortunately, we didn't find any published study on the quinolone determinants in Cameroon. So because of this, we decided to carry out this study on the detection of the QNR gene, plasmid-mediated quinolone-resistant determinants in Cameroon. And we set as objective to identify and describe the antimicrobial resistant profile of Enterobacteriaceae isolates, to detect the presence of quinolone-resistant genes among the quinolone-resistant species, to determine the circulating variants of the various QNR genes, and to find out the relatedness of selected strains of the plasmid-mediated quinolone-resistant gene in E. coli and Klebsiella. So it was a cross-sectional study for a period of 2 years, and we collected 440 specimens from in and out patients at the 3 reference hospitals in Yaoundé. It was made up of 3 phases. The first phase consisted of specimen collection, preliminary analysis, and it was carried out at the Faculty of Medicine and Biomedical Sciences, and specimens were collected from the Yaoundé General Hospital, Yaoundé University Teaching Hospital, Yaoundé Gynecological and Obstetric Hospitals. And these specimens were identified using AP20E and stored in 10% reservoir brain heart efficient agar at -80 until transportation. The phase 2 consisted of phenotypic analysis, that is, these isolates were re-identified in the Center for Enteric Diseases, National Institute for Communicable Diseases in Johannesburg, and then antimicrobial sensitivity was carried out using the VITEC. After that, minimal inhibitory concentration of ciprofloxacin was carried out to determine the quinolone-resistant isolates. And these quinolone-resistant isolates were used for phase 3, which consisted of the genotypic analysis, and it was consisting of our PCR analysis using conventional PCR to identify the quinolone-resistant determinant, and also sequencing, which consisted of the Sanger method, and we also did post-feature electrophoresis to find out the fingerprint relatedness of the isolates. These are our primers that we use as previously described by other researchers. As concerns our finding, we found out that Escherichia coli was the most prevalent with 144 isolates, and this was followed by Klebsiella, 148, and the least prevalent was Serratia and Salmonella genus. In terms of antimicrobial susceptibility testing, our isolates were mostly resistant to ampicillin with 81% resistance rate, and the cephalosporin azacitidine with 48.4%. But the least resistant was to imipenem, and this is because this group of drugs has been reserved for last-line treatment, and so very little resistance rate has been observed in this group of antibiotics. In terms of our resistance strains, resistant isolates, 161 isolates out of the 440 were quinolone resistant after we carried out the e-test, and this was made up of mostly Klebsiella and Escherichia isolates. We detected the plasmid-mediated quinolone resistant gene starting with the QNRA And with the A, we were able to detect only 2 positive, which were both Klebsiella pneumoniae isolates. We went further to detect the QNRB. This one was more prevalent, and we found out that 31 of our isolates were positive for the B gene. And the Klebsiella again was topping the list with 21 positive, and this was followed by Enterobacter, surprisingly, and we had Escherichia coli, and we also had Salmonella. Salmonella normally is very sensitive to the quinolones, and so it really surprised us that some of the Salmonella strains were carrying the quinolone-resistant genes. We went further to detect S, the QNRS, and we found out that 13 were positive, with 3 being E. coli, and Klebsiella again top our list with 10. The QEP gene, which is an efflux pump mechanism, we found out that 3 positives, and these were Klebsiella 1 and E. coli 2. Sorry. We went further to check the amino acid transferase gene, and again, Klebsiella was topping our list with 44, and E. coli 33, and Enterobacter 4. We had other rare species like Pantoya and Proteus also present, and again, Salmonella had 1 isolate which was present with this gene. We went further to compare the E. coli and Klebsiella groups, which were the most prevalent, and we found out that the difference was statistically significant for the QNRP, the QNRS, the amino acid transferase, and then for the gyrase group. For our post-field electrophoresis, we selected a few isolates for Klebsiella because of cost and time, and we did post-field, and we found out that some isolates were closely related to 100%, and when we went further to check the data, we realized that these isolates were from the same hospital. The first pair, that's 162 and 361, were from the same hospital, which means that there is a transfer of gene within the same hospitals and within the patients. And we also found out that the other pair of Klebsiella isolates, 051 and 057, were also from another hospital, the same hospital, and were closely related. For the E. coli, the E. coli strains were not closely related, and we found out that most of them were from outpatients, which indicates that E. coli is usually a community-acquired infection, and unlike Klebsiella, which is mostly acquired from the hospital environment. In terms of conclusion, the quinolone resistance in Enterobacteriaceae was high in clinical isolates. These isolates have evolved resistance through multiple mechanisms, harboring several quinolone-resistant genes, and we will need strategies in Cameroon to limit the spread of these quinolone-resistant Enterobacteriaceae genes, which need to be deployed to conserve quinolone effectiveness and promote alternatives to their use, especially in farming and with agriculture. Sorry. I would like to thank the sponsor for this work. That's the Organization for Women in Science for Developing Well, and our host, the National Institute for Communicable Diseases, and the university, I would like to borrow the slogan of WHO, which is no action today, no cure tomorrow. Let us combat drug resistance. Thank you very much for your attention.
Thank you so much, Dr. Emilia, for your wonderful presentation. Thank you so much. If you've got any questions, you can post them in the question and answers chat. And alternatively, you can wait at the end of the session to pose your question to the presenter. Okay, so our next speaker is one of the students from the Northwest-University, and the student is Daniel Ajose. The student will present to us about whole genome sequence analysis of the multi-drug resistant bovine mastitis pathogens and assessment of the plant-derived nanoparticles as a biocontrol agent. Over to you, Daniel.
Thank you, Doc. Okay, can we see my screen? Hello?
Not yet. Maybe it's, oh, there we go. You can just maximize, put in the presentation mode.
Awesome. Okay, how about now?
Yes, you may start.
Okay. Thank you very much for this opportunity. I appreciate this. I am Ajose Daniel, and I'll be presenting my PhD proposal titled Whole Genome Sequence Analysis of Multi-Drug Resistant Bovine Mastitis Pathogens and Assessment of Plant-Derived Nanoparticles as Biocontrol Agents. This is the outline of my presentation, a brief introduction with including the statement of problem, justification and objectives, the methodology, acknowledgements, references, and conclusion. Just to start with, bovine mastitis. What is bovine mastitis? Bovine mastitis is a condition which is characterized by an inflammation of the udder of the animal. It is caused by various factors such as contagious or environmental pathogens, nutrition and general management conditions of the farm. The significance of bovine mastitis, its effect ranges from animal welfare to industry economics, some of which include but not limited to milk yield and raises in milk production costs by wasting milk, incurring preventative costs and therapeutic costs, and also premature culling. The causative agents include a wide range of microorganisms, including the gram-positive and gram-negative bacteria. The most common causes in cattle mastitis are Staphylococcus aureus, coagulase-negative staphylococci, Escherichia coli, and other coliforms. So just moving straight to problem statements. Antibiotics have long been considered the first line of defense against bacterial infections in dairy cattle, especially in mastitis. However, there are some shortcomings associated with this treatment method. And these shortcomings include low cure rates, presence of residues in the milk and meat of treated cows, and the proliferation of multi-drug resistant bacteria, which is a pressing public health concern for animal and human, and of course, food security and development. And also from the One Health perspective, mastitis causing bacteria have broken through a number of hierarchical barriers, allowing for zoonotic transmission from bovines to people via contaminated milk and meat. And as such, the disease control has been a quite challenging one, hence the call for alternative therapy. And when we talk about alternative therapy as related to this study, we are looking at ethno-veterinary medicine, which is the application of indigenous knowledge in treating animal diseases, and also nanotechnology. The use of nanotechnology as an alternative to antibiotics has gained significant recognition in recent times, being a promising tool for use in medicine and agriculture. Thus, we move to the justification of this study. Considering the aforementioned, this study is intended to ascertain the mechanism of action of selected indigenous plant extracts and devise a therapy that would prevent or repair damage to alveoli structure, thereby maximizing succeeding secretory cell differentiation. And moreover, in meeting the National Development Plan of South Africa, especially goal number 3, which is raising economic growth and promoting exports, and also the Sustainable Development Goals, specifically goal number 3 and number 12, which talks about good health and well-being, and also responsible consumption and production, respectively. The use of natural and sustainable local resources for combating animal diseases is thus imperative to improving milk and farmers' yield, animal and human health, and bringing about low production costs as a result of low preventative or therapeutic costs. So I move on to the objectives. The aim of this study is to determine the in vitro efficacy of plant-derived nanoparticles against multi-drug resistant bovine mastitis pathogens, and specifically to isolate and characterize the multi-drug resistant bovine mastitis pathogens using whole genome sequencing and determine the antibiotic profile of the pathogens, and also to evaluate the antibacterial efficacy of plant extracts against the isolated multi-drug pathogens, characterize the phytochemical constituents of the extract, synthesize nanoparticles from the extract, establish their antibacterial effects and mechanism of action, and lastly, to determine the biocontrol potentials of the derived nanoparticles against the multi-drug pathogens using a simulated experiment with bovine teat canal epithelial cells. So going to the methodology. Firstly, the Faculty of Natural and Agricultural Sciences Research Ethics Committee will be consulted for ethical clearance. And upon this, or following this, sample collection will begin. And of course, the sample collection will be followed strictly. The necessary conditions will be followed strictly. And after sample collection, the samples will be brought down to the laboratory under the recommended conditions for analysis. Then isolation and characterization of the bacterial strains, selective media to include mannitol salt agar, blood agar, conky agar, and eosin-methylene blue agar will be used respectively to culture Staphylococcus aureus, Strep agalactae, Klebsiella pneumoniae, and Escherichia coli. And of course, each colony will be examined for microscopic characteristics, then the biochemical test to include the sugar fermentation test and oxidase, and also the gram staining will be done on the isolates. The antimicrobial susceptibility testing and examination of minimum inhibitory concentration. This will be done following the disk diffusion method as earlier described. Then the zones of diameter will be measured aseptically using the standard method, and breakpoint values will be interpreted using the Clinical and Laboratory Standards Institute method of interpretation, which is the latest one, CLSI 2021. Then multiple antibiotic resistant phenotypes will be generated from the isolates that show resistance to 3 or more antibiotics. Molecular identification of the multi-drug isolates. Here, the extraction of the DNA from the bacterial colonies will first be done, and this will be done using the Zymo Research Genomic Kits following the manufacturer's instructions. Then the polymerase chain reaction amplification will also be done on the isolates based on the 16S and using the universal primers. Using the universal primers of 16S, then the specific primers for each of those isolates. Then whole genome sequencing will be done, and this is to provide more information on the pathogenicity of the isolates and the identification and even the epidemiological typing and drug susceptibility, because these are very crucial and important. Whole genome sequencing will be employed because it allows the sequence of thousands of genes from hundreds of microorganisms. Plant collection, extraction, and characterization. Some listed plants will be used in this study, and these plants are Melianthus gomosus major, Dodone, Angostiglia, and Carponia aurea. And these plants have been selected on the basis for their use in similar conditions in traditional medicine, and also on the basis of their nativity, availability, and based on the fact that they are plants of least concern. And the selected plant part that will be used in this study is the leaf. And this is because the leaf is a sustainable resource from field. Then after this, the authentication will be done at the herbarium section of the Department of Biological Sciences, and voucher specimens will be dropped there. Extraction and characterization procedures will be done as earlier described by previous scientists. Then determination of minimum inhibitory concentration. This will be done using the micro broth dilution method as earlier described. And here we'll be using the microtiter plates to determine the minimum inhibitory concentration of the extract. The negative control will be used, and all experiments will be done in triplicates. And then will be read using the spectrophotometer. Green synthesis of the nanoparticles characterization and antibacterial activity. Here for the green synthesis, we are going to use the green synthesis because it is a preferable alternative to the physical and chemical methods, as it is eco-friendly. And silver nanoparticles will be synthesized from the extract, as previously stated. The reason for choosing silver as the metal of choice here is because it has an effective role as an antimicrobial agent. It also actively selects over potential pathogens, but not over symbiotic microbial communities. And it also has a low toxic effect over the animal and human consumers. And lastly, it has a low risk of environmental pollution. So characterization of the synthesized nanoparticles will be done as described by Zhang et al. In 2016. And the characterization will be done based on, using different analytical methods to include the FTIR, which detects small absorbance changes, and scanning electron microscopy, which looks out for size distributions, shape, and surface morphology. Antibacterial activity of nanoparticles. The antibacterial activity will be carried out using the microbroth dilution method as well. And here the minimum inhibitory concentration and bactericidal concentration will be determined. The choice of antibiotic that will be used as a positive control will be dependent on the results of the antibiotic.
I have to wrap your work. You're left with 2 minutes. Sorry for disturbance.
Okay, thank you. So for the mechanism of action of my nanoparticles, this will be achieved as described earlier. And of course, the reactive oxygen species levels will also be measured. Then for the simulation experiments, under the cytotoxicity, inflammatory cells will be exposed to nanoparticles to elicit inflammation by forming reactive oxygen species that will generate oxidative DNA changes. And this will be studied following methods as described by Kalinska et al. And the bovine mammary gland cell lines will be used for this study. And for the apoptosis, viability of cell line will be determined using Presto Blue as stated also by Kalinska et al. Then there will be a control group which will consist of cells kept in a medium without the addition of nanoparticles, and absorbance will be read using the wavelength of 570 nanometer. Then following all of this, statistical analysis will be done where data will be presented as means of standard errors. Then acknowledgements. I acknowledge all members of my supervisory team, Professor Sien Ateba, Professor Aremu, Professor Fayemi, staff and members of the department, and even the postdoctoral fellows within the department, and all members of the antimicrobial resistance and field bowel control research group. Here are the selected references. Thank you all for listening. I appreciate it.
Thank you, Daniel, for the nice presentation. We'll now then move over to another student. Then the next presenter is Christ Donald. I'm sorry, I cannot pronounce your surname. Maybe you can pronounce it to us whenever you start. So Christ Donald, you're the next speaker. You can share your presentation.
Myself. Can you hear me?
Your line is more like speaking, Christ.
I really don't know what is happening.
We can hear you. You can just share your screen. There we go. You can just maximize your screen.
Sorry?
Guys, can you put your presentation in PowerPoint in a presentation mode?
Hello?
Your PowerPoint
Yes.
in a presentation mode. Can you
Is
maximize
it
your
not in the presentation mode already?
There we go. Now it's in presentation mode. There you can go ahead.
So
Thank you.
Okay. Okay, thank you. I'm Chris Donald Captron. I'm a student supervisor, a PhD student supervised by Prof. Teba, and then the topic I'm going to address to you today is the evidence of virulent mutational resistance and biofilm forming Listeria species in South Africa food chain, the potential public health implication. This will be my outline. As an introduction, Listeria has been discovered for the first time by Moore in 1924 due to the death of 6 young rabbits. In 1927, Piri isolated from livers and he named them Listeria hepatolytica. In 1929, isolated was confirmed in human by Smith and Neufeld, isolated in infectious mononucleosis from 3 patients. In 1940, Selgeri finally named the organism as Listeria monocytogenes. Listeria is a gram-positive for non-spoiling forming, which measures 0.4 to 0.5 micrometer of diameter, is ubiquitous in nature, motile, non-capsule and motile by petri dish flight. The genus is classified under the family of Listeriaceae, and the growth condition are from 0 to 45 degrees Celsius. The optimum temperature of growth is 30 to 37, and the salt tolerance is 10%. Listeria can survive under a pH being 4 to 9. We have 6 main species of Listeria, where Listeria monocytogenes is pathogenic to human, Listeria ivanovi pathogenic to animal, and Listeria inocuea. Listeria ivanovi pathogenic to animal, and Listeria silgeri, Listeria wetmari, Listeria grey, which is some of the names of some of the genus species. Listeriosis is a worldwide foodborne disease with a high fatality with a mortality rate of 20 to 30%. Processed food may get contaminated during the production from the raw product to the final consumer. In addition, this affects public health and economic status of particular countries. Good manufacturing practice must be strictly followed to identify the critical point where there is high risk of contamination. The consumption of the contaminated food is the main route of transmission to human. Here on the picture, we can clearly see that they are being some chicken, and from there, if the agent is properly conducted, we can easily get biofilm. The biofilm can be formed at that level, and the contamination can come from the facility, from the equipment, from the personnel, or from the material that they are using to cut the chicken. From the surface, Listeria is capable of producing biofilm, are a community of bacteria that produce
Are you still there? Seems like we're losing him. Christ, Donald? Okay. We are struggling to hear your sound. Can you unmute yourself, Donald?
Yes. Is it done?
Yeah, we may proceed now.
The pathogenic characteristic of Listeria is Listeria is able to invade the mammalian cell to escape from phagocytic vacuole to grow in the host cell cytoplasm. It's an intracellular motility and move cell to cell. We have some major virulence genes which are hemolysin, phospholipase, ACT-A, and internalin. Sorry. It's happening. Okay. Here is just a representation of how the Listeria monocytogens are moving in the cells. And then we can see that they are propulsed by the ACT-A. And this other one is more clear because it has been taken with microscope electrophoresis light. The symptom of listeriosis is fever, muscle ache, nausea, and diarrhea. Severe symptoms are meningitis, mental change, brain abscess, or way to death. Who is at risk to contact listeriosis? The people who are at risk to contact listeriosis are pregnant women, older adults, and people with weak immune system. We have tried to gather some information for the last day of white. And here we clearly see that the product since 1990 was involved in the George Kelly dairy product that was involved in. Here we have the fish food product that was involved in the listeriosis. In 2011, we got 147 cases of listeriosis with link in USA in Jensen Farm, and the product that was linked to that listeriosis outbreak was the melon.
5 minutes remaining.
The frozen vegetable was also recalled in UK in July 2018 because, sorry?
I was saying you left with 5 minutes for this presentation. You may continue. You may continue. Just know that you're running out of time. Just continue.
I just have to rush. Recently, the USA
Seems like he's having an unstable network issues. I hope we'll be able to regain him. So I think we're having difficulties in getting Christ Donald. I think we have to cut it here and maybe move over to another presenter because it's going to keep on doing the same thing. So thank you guys. Unfortunately, we're going to have to move to the next presenter. So we got already presented this in the first session. So we will now move over to the PhD student. Can everybody hear me? My internet was also not stable. So the next, okay. Yeah, so the next presenter is a student. It's Bukola Opoyemi Oluwarinde. This is a PhD student at the Northwest University, and the student will be presenting to us a comparative study of biocontrol, potentials of bacteriophage, adhesion, and tenets against multi-drug resistant bacterial bovine respiratory disease pathogens. Over to you, Bukola. You may share your screen. Bukola, are you here?
Yes, I am here.
Yes.
Yes. Can everyone hear me?
Yeah. There we go.
Okay, thank you. Yeah, my name is Oluwarinde Bukola Opoyemi, and I will be presenting a comparative study of the biocontrol potentials of bacteriophage adhesins and tannins against multi-drug resistant bacterial bovine respiratory disease pathogens. This will be a proposal presentation. This is my outline of the study. Okay, introduction. Bovine respiratory disease continues to be one of the main threats to young cattle's lives and has a major financial impact on various cattle production systems. Several viral or bacterial agents are responsible for bovine respiratory disease, and interactions occur amongst the agents. Antimicrobial antibiotic resistance due to long-term treatment of BRD infection by the use of antibiotics. These pathogens have developed resistance to antibiotics. And also, because of this, we are introducing bacteriophages, and bacteriophages are a natural enemy of bacteria and a natural biocontrol agent of bacterial pathogens. And the interesting thing about phages is that they are highly specific, hence their effectiveness as on-target organisms. Also, bacteriophages possess adhesins. Adhesins are proteins on phage surfaces, which are used in the adherence to bacterial cells, and they are primarily responsible for phage adsorption specificity. Major advantages of phage therapy is their specificity, like I just said. Aside from bacteriophages, we are also going to be including tannins, which are naturally occurring water-soluble polyphenolic compounds. They also possess antibacterial activity and anti-biofilm properties. It's interesting to note that tannins bind to bacterial outer membrane proteins. They inhibit cell wall and nucleic acid synthesis. Hence, this is why we are also going to be using them in this study. The problem statements. Livestock, especially cattle, are important assets in Africa. BRD complex is one of the major problems affecting cattle worldwide. Their prevalence of these diseases, has caused increased rate of cattle morbidity, mortality, and reduced agricultural production, unfortunately. Strains of BRDs, like I said earlier, have developed resistance to several antibiotics, thus the need to assess antimicrobial resistance and virulence gene profile of this isolates. So significance of this study, the use of lytic phages and tannin from seaweed extracts as biocontrol agents will improve animal husbandry. Then the mechanism of action of phage adhesins and tannins will be further understood, and being the first study of its kind, the data generated from this study may serve as a baseline for further studies on the use of phages and tannins. Hence, the aim of this research will be to perform a comparative analysis of the biocontrol potentials of bacteriophage adhesins and tannins against multi-drug resistant pathogens. These are the objectives of the study. Methodology. Isolation of bacterial pathogens. This will be done using the brain arts infusion agar with 7% blood. All isolated presumptive microorganisms will be purified. Gram staining will be done and other biochemical tests. Molecular identification will also be carried out using specific primers to identify the organisms, after which antimicrobial susceptibility pattern tests will be carried out on all of these pathogens that are isolated using the CLSI 2021 standard. For the isolation of the BRD pathogen-specific bacteriophages, phages will be isolated from wastewater samples obtained from abattoirs using the control strains of all 3 BRD bacterial pathogens. And this is because the wastewater samples will be used because, like I said before, phages are highly specific, so we need to get them from the same environment where the pathogens were isolated from, which is from the cattle. So the wastewater samples from abattoirs will be used in this state. And about 1 liter of the wastewater will be obtained. This will be moved to the laboratory. This will be homogenized for about 3 hours and centrifuged. This will be filtered, and then the wastewater sample together with the filtrate now together with the bacterial culture will be put on the shaker, and this will be done to swelled and poured onto agar plates method. Hence, this is called the double agar plate method that will be used in phage isolation. After isolating our phages, we are going to characterize them. We're characterizing them using the host range determination. We'll determine the host range of the phages. We're also going to check the plaque morphology, that is the size, the edge, and the boundaries. We're going to also check the stability of phages in different conditions, which is the temperature, the pH, and UV. And we'll do all of this to get an optimum condition in which the best condition in which our phages is going to show the activity against the bacterial pathogens. Whole genome sequencing will also be done to determine the safety potential of phages. Whole genome sequencing will be done. Then we're also going to carry out a transcriptomic analysis of the BRD pathogen response to phage infection, where the ultranscriptomic sequencing will be done following the method described by Searcher et al. 2018 to understand the interaction between the bacterial pathogens and the phages. Tannin extraction and characterization will also be carried out. Tannin will be extracted from seaweed using the microwave-assisted extraction technique following the procedure described by Hong and Lee 2011. For adhesine production and purification, adhesines will be produced and purified following the modified method of Mernikiewicz et al. 2012. Briefly, virgins encoding short-tail fiber adhesines and chaperone will be cloned on an expression plasmid. The vector will be expressed in the bacterial expression using E. coli. Then PCR will be used to amplify the adhesine genes using appropriate primers. Produced adhesines will be further purified using the Coulomb gel, and all of these procedures will be monitored using the SDS patch. After the production of adhesines, we are going to carry out a simulated experiment showing the effect of adhesines and bacteriophages and bacteriophage adhesines and seaweed tannins, seaweed tannins and phage adhesines on the bacterial pathogens. Here, epithelial cells will be used. These epithelial cells will be grown together with the BRD pathogens now in 96 well plates. This will be incubated for 24 hours, after which phage adhesines and seaweed tannins will be incubated alongside with this mixture for 72 hours. And after 72 hours of incubation, we will check the readings on the microtiter with the microtiter plate reader. And here we're going to check for binding and cell death. Statistical analysis will be done. Every data obtained will be presented as means plus or minus standard errors of the means. Analysis of variance followed by 2-key process for the significance will be performed using the SPSS statistical software package. So for the expected result, we hope to issue information on the use of bacteriophages and tannins as an alternative to conventional antibiotic in the treatment of BRD infections. Here are my references, and thank you for listening to me.
Thank you so much, Ogola, for the nice presentation. It was well informative. We're now going to be moving to the next keynote speaker, which is Dr. DMT Mtiani. Is Dr. Mtiani here? So just a brief the biography of, no, we don't have a biography of Dr. Mtiani. So, but if Dr. Mtiani is here, Dr. Mtiani is a doctor from the Northwest-University, Dr. Mtiani is based at the Department of Animal Science, School of Agricultural Science at the Faculty of Natural and Agricultural Sciences. So over to you, Dr. Mtiani, if you're here. Mtiani, are you here? Are we getting Dr. Mtiani? Seems like Dr. Mtiani is not here.
Okay, I'm just trying to get hold of him, Dr. Lekota. Just give me 1 minute.
Okay.
He says you should unmute him. He says he is muted.
Panelists, can you try by all means to unmute him?
I can't see him online on my side, and they can unmute themselves. So I don't see him online on my side. Unless he logged in with a different name.
So there was a one presenter as well that I think she left us. She's supposed to be joining us at 12. Maybe perhaps we should move over to that keynote speaker.
Yeah, he's there. Dr. Lekota, he's in, but I don't know the name he's using when he logged in, because I can't see him there. Even on the panelist list, he's not.
Okay.
So he says he's just logging in and out again now, because he says he's in the office.
Can I just have maybe a confirmation if Dr. Agebe is here? Dr. Agebe, are you here? Or even the speaker is not available.
Let me just also try to phone him.
Okay, while we're waiting for that, I think yes, that's a good suggestion. If we're still waiting for the other two speakers to come on board, maybe we could open this session for questions to the presenters, the key speakers that presented in this second session. And then as soon as they are available, then we can move over to the other two key speakers. The floor now is open for questions for the second session presenters. If there's any question, you're more than welcome to raise your hand. Raise your hand, then we'll attend, the speakers will directly attend to your question. Please help me if there's any hand that is up, and then you can just unmute yourself and ask. Okay. Maybe I could start maybe with, who's this, Daniel? Is Daniel here at Jose? I just want to find out your project. Can you maybe just clarify based on the whole genome sequencing and metagenomics approach that you're intending to do? Are you planning to do both of them, or the study is only based on whole genome sequencing from pure cultures? Because there's no much, I just want to understand if your approach is on the right direction.
Yes, thanks, Doc. It's just on whole genome sequencing.
And then do you have any criteria in terms of how you're planning to do your whole genome sequencing? Any amount of samples, considering that whole genome sequencing can be, it's more expensive?
Yes, it's more expensive, but we are looking at having a collaboration with those that will help us with it.
Then you're planning to sequence everything that you find there?
We'll just pick the multi-drug resistant ones.
Oh, okay, that's a good one.
Thank you, sir.
Okay, my question is it's now on Christ Donald. Can you just clarify in terms of how does phagocytosis, how does the phagocytic vacuoles of the bacteria able to escape in the cells? Are there any specific genes linked to different pathway, or it's just one genes? What is the involvement of the regulation of genes that enables the bacterium to survive the vacuoles?
Thanks, Doc. I'm sorry that I could not finish the presentation for me to explain everything clearly. I was kicked out because my internet was having a problem. There's one gene that is involved in the spreading of the cells of Listeria from one cell to another. That gene is named ACT-A. And during our research, the outcome of the research that we have done, we have picked quite a number of those genes, or those virulence genes. And we also isolated a lot of Listeria monocytogenes. I don't know if I have answered clearly your question.
Yes, you
that
did.
ACT-A is the actin.
So it doesn't have any involvement with any other regulons or any other genes in there? Is it just only one gene that is?
As far as I know, it's only that gene that is involved on it.
Right.
We do have the other virulence gene, because it's a process. We do have other virulence genes that are working in the cells for the Listeria, the pathogen Listeria to mature before moving from one cell to another.
All right, thank you. We had also a presenter called Pukola. That's a nice presentation about the usage of bacteriophages for biocontrol. Just for interest's sake, at what stage, let me just say you have an animal that has that clinical symptom. At what stage where are you planning, or when are you planning to introduce the bacteriophages? So the animals there, it shows the clinical symptoms, but at what specific stage do you think you can implement the bacteriophages for biocontrol?
Okay, to get your question right, you're asking, when am I going to use the bacteriophages?
Yes.
Okay, the thing is, first of all, every pathogen I'm going to be using are going to be pathogens that are multi-drug resistant. So these multi-drug resistant isolates are the ones that I'm going to treat with, or rather that I'm going to effect with bacteriophages.
Yes.
Yes.
But what I'm asking is now, if you have a live animal, maybe that shows that clinical symptoms, it's tested with those pathogens, but at what stage, if you have to implement the bacteriophage in the environment, at what specific stage?
Okay, I think I get what you're saying. I'm not so sure if the use of bacteriophage in live animals now is practicable now in South Africa that we know it. Yeah, although even if it's going to happen, it's going to be probably when the phages are encapsulated, you know. However, in live animals now, I don't think it's. I'm not seeing where we use phages on live animals.
I know you're doing in vivo, but how about in vitro? What's going to happen? Anyway, so is there any specific use? Why are you focusing on lytic phages? Why is there any ignorance in terms of lysogenic phages?
No. There's no major reason for that. We're just focusing on the lytic phages because we actually wanted to we want to see its effect on these pathogens. Yeah.
So then how do you go about isolating the adhesion of the phages? I'm just interested for interest's sake, because I've never done that. Like, how do you go about isolating this specific sides, like you're looking at the adhesion? How do you go about doing that?
Yeah, for the adhesins, actually, when I was trying to go read about adhesin production, how it's being done and all, from literature, I found out that they use, what's it called now? Genes coding adhesins and chaperone. Then we use the expression plasmid now and a vector to express these genes, then put them in the host, you know, then we now use the PCR method to ensure that, okay, this host has the genes, then we now use the phages.
Okay.
Yeah. So I'm still doing my research on that particular methodology. However, that was what I was able to get when I was reading about it. But I know by the time I get to that particular stage, I will figure it out. Totally. Yeah.
There's also some questions on the floor. If the speakers that presented as well, please attend to the questions and answers that are posted in the chat for question and answers. There's a question.
Okay, so I see a question. Yeah, I see a question that says, how am I going to differentiate the live cells and dead cells in a microtiter plate reader? For that, we can detect a viable cell using the Presco blue tests. So when we use the dye stain while conducting the tests, the change in colors, now the difference in colors will differentiate the live cell from the dead cells. Yeah. That should also apply to.
Oh, I hope that answers you, Apiwe, in the chat. Is there any other questions on the floor? The floor is still open for questions. You can raise your hand, then we'll attend to you if there's any question. Okay, I think apparently there's Dr. Mtiani raised their hand. Mitiani, if you are available, I think maybe we can move over to you. If you are in this webinar, I think we can now proceed to your presentation. Can you kindly share your presentation? Mtiani, are you here? Dr. Mtiani, are you here? Abolo, but Bukolo, I think there's also a question. Okay, maybe this question is directed to Sidana from Cameroon. They're saying, what have you chosen? What? I'm not sure if the question is what or why.
I saw the question. I was almost replying on the chat. However, I chose tannins because, first of all, they delayed the development of resistance in bacterial pathogens, with the help of their antibiofilm properties. We know that what we are discussing now is about antibacterial resistance. So tannins have shown to show such property, and also their mechanism of action is a very interesting one, whereby they bind to bacterial outer membrane proteins and inhibit cell wall and nucleic acid synthesis. So we know that even if these organisms, these pathogens are antimicrobial resistant, the tannin should be able to do justice to them as well. So hence that was why we chose tannins.
Thank you for answering that. I hope maybe we're almost getting towards getting the other speakers available. If there's any of the speakers that are left that didn't present, please just indicate if you are available in the room so that you may proceed. Just for clarification, we have Dr. Akebe Luther King. We are waiting for the speaker to show up and present. Dr. Mtiani as well is another speaker. That
Dr. Akebe Luther King is available.
Can you kindly share your screen?
Okay, just doing that now. Okay, yeah. Is it visible now?
No, we are unable to see your screen.
Okay.
There we
there we go.
There we go. Just some informative background about Dr. Luther King. He completed his PhD at the Tshwane University of Technology under the Water Microbiology Research Group. He was also a postdoc research fellow at the WAAW University, and he's currently a leader of the molecular and environmental surveillance of the antimicrobial resistance sections of the microbial research unit at the University of KwaZulu-Natal. Over to you, Luther.
Thank you very much. Good day, ladies and gentlemen. And I see we've had a lot of issues with network. I've also been having some issues with that. I hope we'll be able to go through the presentation fluently. So I'm presenting today on environmental antimicrobial resistance, the neglected piece in the One Health puzzle for combating AMR. And all these names that are down here, their work is a combination of evidence of what we've done so far, revealing the importance of the environment in the transmission of AMR and how this is affected by other sectors like humans and the animal, especially the animals. So I would like to first of all point out that I'm not going to be talking about mechanism of resistance. I've followed the other presentations and these ones have been done, and the views are absolutely mine and my work, so should not be associated to my institution when citing or quoting that. And also in some cases, you might not have some of the names of the places because this was due to the agreement with the site. So briefly, the Antimicrobial Research Unit is focusing on One Health, and we all know what the definition of the One Health is, which is summarized as recognizing the interconnection between people, humans, and the environment. And so since this has been placed as the main way of targeting disease and antimicrobial resistance in particular, that has been the focus of the ARU and where I lead the molecular and environmental surveillance. as clearly mentioned, under the directorship of Professor Sabia Isaac. And we do this, whatever we do in the environment, humans and animals, we do this using culture-based techniques and advanced molecular techniques like metagenomics and whole genome sequencing. So just to discuss a little bit, I come from a place called Basa Industrial Area, Douala. That is where my family house is. And you may ask yourself why I'm saying this. This place is highly industrialized, which means that there is a heavy industrial pollution occurring that place with a lot of chemicals being sent into the environment. And it's a very densely populated, but the problem is that that area is mostly swampy with a shallow water table at times below less than even 40 centimeters. You just get water coming out already from the ground. No sewage system in this area, mostly pit toilets, well, and poor access to pipe-borne water. So mostly boreholes are being used in this area. So why am I talking about this place? In this place, that is my beautiful mother standing in front of what used to be our house. And if we look around here, there is a water course going in this area. And why would I be talking about my mother? When I was growing up in this area, we had our backyard poultry farm and piggery, but the feed was expensive, and so we couldn't afford buying the feed. So we tried to search out with our little knowledge, and we resorted to producing our own feed. So we use corn, crayfish. For those who come from this side, they will understand what, from the west side, they will understand what I mean by crayfish. And one thing that I knew at that time was that we were putting red and yellow capsule and a certain tablet that was called 760. Until today, you wouldn't ask me 760 and I'll tell you the scientific name of it. But I later on discovered that the red and yellow capsule that we were using was amoxicillin. The washing from the chicken house and the pot and the piggery were all sent into this water course. So everything was going down there. And the litter that was coming out was just going into a corn farm that was just next by. So that was just a small portion of a backyard poultry. But currently, after studying, I now started working with the Antimicrobial Research Unit, where we carried out this study to find out on the antimicrobial resistance in the animal sector using the farm-to-fork approach. And what did we see in this present work? We tested our isolate against 12 antibiotics, and we found out that 37% of the enteropococci in the poultry farming were multi-drug resistant. We also did similar works with pigs, and we tested 20 antibiotics against E. coli, and we found again that 71% of our isolates were all multi-drug resistant. This was in animal farming. Now, this was at industrial scale animal farming. However, what was the cause of this resistance? The bad thing about it is that antimicrobial use in the animal sector has actually been banned in most of the European countries, but unfortunately in Africa, we still have it. And the South African document regulating the use of antimicrobials in animals still allows the use of some of these antimicrobials. And also where they are not directly used, we have like homologs, like the oxytetracycline that is used for tetracycline, and we have the enrofloxacin that is used, which has the same mechanism as ciprofloxacin. So these all generate co-resistance or resistant to similar drugs which are used for human medicine. So when these antibiotics are used in the animals, what happens? It doesn't end there. We went further to carry out this study in which we decided to evaluate the litter that came from the same poultry where we had earlier sampled and seen a high resistance. We wanted to see if the resistance which we saw in the poultry was transferred to the environment. So we followed the manure that left from the poultry into this sugarcane farm where it was spread at industrial scale. Where it was spread at industrial scale. So what did we see? We realized that out of 835 enterococci isolates that we isolated, pure isolate that we got, we had 56% of them that were resistant to at least one of the antibiotics that we tested. And we also realized that amended soil, that's manure amended soil, had more resistant bacteria compared to unamended soil, as we could see a significant difference of about 67% against 10% for unamended soil. Then we also looked at wastewater treatment plants in that same locality where the sugarcane farm is located, where the pig farm is located, where the animal farm is, the poultry farm is located, because we know that these wastewater treatment plants are the ones that service the whole of that area together with the hospitals. And what we did again in this study is that we isolated 579 enterococci and 560 E. coli, tested them against different antibiotic panels based on the AGISA protocol. And what did we see? We realized that after isolating these organisms, if we take the enterococcus, for example, we realized that doing a phylogenetic relationship with other isolates from Africa, that's our environmental isolates with other isolates from Africa and in South Africa, we picked up this. We first of all found 3 major clusters, and within the first cluster, major cluster, we realized that there was a link between river isolates, wastewater isolates, and soil isolates, which means there was an interconnection between these 3 systems. But interestingly also, within South Africa, we still found that there was still soil and water. Another interesting thing that we realized is it doesn't just limit to South Africa, but we found out that we had human isolates linking with our soil isolates within South Africa, showing the connection between humans, animals, and the environment on antimicrobial resistance. So if we have seen antimicrobial resistance in the environment, so what? Some years back, during my PhD, I searched for antimicrobial resistant bacteria in water. But while most work focus and look at them in the water column, it's possible that if it's coming out from a wastewater treatment plant, we might miss it, because most of the at times the bacteria are injured. So when we grow them, they don't. But they settle down into the sediments, and there they can recover and they grow. And sediments have been known to contain more antibiotics and more nutrients and more bacteria than the other thing. And what did I find? I realized that there was a high concentration of antimicrobial resistant bacteria within the sediment compared to the water column. And it has been shown that there's a higher antimicrobial resistant genes concentration, and therefore the possibility of higher chances of horizontal gene transfer occurring within the sediments compared to the water column. So what does that mean then? If we have seen the bacteria inside there, they could be there today and tomorrow they are dead. So this other study which I carried out was to see how long, therefore, E. coli, Vibrio, Salmonella, and Shigella, for example, would survive within the environment, within water and sediment. And what did I realize? I realized that looking at the T90 of Vibrio, for example, at 20 degrees, which are temperatures that we get within South Africa, between 20 and 30 degrees, the organisms could survive in sediments for up to 32 days. Now, what does that mean? 32 days means that if a wastewater treatment plant, because this was done on the Apis River, where there are 4 major wastewater treatment plants, if a wastewater treatment plant will fail, as somebody rightly said, that although South Africa has all these wastewater treatment plants, most of them are also not working. So if any of the treatment plants was to fail just once a month, it therefore means that we will have a constant supply of bacteria within our environment. So 30 days in a month, we will have bacteria if the water plant fails just once a month, because Vibrio could survive up to 32 days within the sediments inside the environment. So they could survive, it's true, but we don't have any interaction with that water. What is the problem then? So I went further to look at, will this therefore be resuspended if it was disturbed? And in this case, 2 scenarios were looked. A natural scenario where cows were meant to cross, this was in Botswana, around the north of Pretoria, towards the north end of northwest end, closer to Pretoria. And it was also observed that disturbance of the sediments, whether mechanically when people go in there to wash their clothes, like in places where we don't have water, or by cattle that were crossing, caused the resuspension of the bacteria that were inside the sediments, including the antimicrobial resistant ones. So if they get resuspended, what is the case again? So I say, and so what? They are in the environment, they can't survive, they can't be resuspended, and so what? It still doesn't cause any problem. So what is the thing? So what therefore is the problem here? First, it comes from the animals, it goes to the environment and then goes back to the animals. But how does it concern humans? Because it is in the water, it doesn't concern us, that water is dirty. But then South Africa has been, we all know, for those who have been in South Africa and those who have been following over the media, have been following it even on the US news, our taps are going dry. Our dams are getting empty, which means that we need to resort now to areas where we need to get alternative water sources. And these, most of the time, are rivers. But these rivers are polluted. And informal settlements at times have only this river as the source of water they have. So while these people here would be having, this is one of the sampling points which I had, while they only have this to play around, the kids in the villages only have this as their swimming pools. So what does it bring us to? We now look at quantitative microbial risk assessment to see what would be the potential risk of infection if someone was exposed to risk-suspended sediments from water. And what we realized is that under condition of on-risk suspension, the percentage was high, but not as high as when the sediments were disturbed. When the sediments were disturbed, we had approximately 100% chances that anybody that is exposed to 1 meal, just 1 meal of water from that environment is likely going to develop a gastrointestinal infection because we use diarrheogenic E. coli as our marker. So how does it concern us then? It therefore means that water that we use is where we abstract our drinking water, even for those, even if we don't talk about the local people or the informal settlement and all the villages, but we realize that antibiotics have already been detected in drinking water, which means that even if we are not going to that river, the water that is abstracted from that river and treated to send back to us, we are definitely going to be having problems with the water that we get from our taps. And some works have already shown that the pharmaceuticals were found in tap waters, like this WRC project that was reported. And even if, I've been talking about water, I've been talking about soil, even if we were to be free from our soil and our water, we are not safe from the air because it has also been reported that antimicrobial resistant bacteria and antimicrobial resistant genes are full in the air. And unfortunately, within South Africa, we are not testing the air yet to find out that which is a loophole that we need to start looking around, especially around our wastewater treatment plants. What could be the reason for not testing the environment all the time? We will see that most of the research that we have been doing is so based on animals, so based on humans. It's because environmental conditions are so complex that not only antibiotics presence in the environment will trigger probably the development of resistance, but we have other stress factors. We have chemicals coming in, we have UV light, we have abundant nutrients, we have other parameters that are so complex. And so it's kind of like scare away a lot of people from working from that point. Whereas in humans, it would be easier to say, if we have resistance to one thing, then we need to stop. Let's say that the use of that, we need to control that. But in the environment, it is different. So the environmental component in the One Health is so complex that it needs further research and more research to be geared towards that so that we can have a better fight against antimicrobial resistance. So what would we say therefore about a possible solution now that we know that our environment is the way it is, and yet it is the least studied when it comes to antimicrobial resistance? We need to, first of all, recognize that AMR in the environment is very, very complex. We need to understand that it is not just because of antibiotics, and more to that, we cannot stop the use of antibiotics. Wastewater treatment plants do not remove the antibiotics, so we will definitely have them discharged in the environment. And many studies have also shown that they will also discharge antimicrobial resistant bacteria. So what we need is that we need to create greater awareness in medical and veterinary practitioners, because they may not understand the environmental impact of the prescription of antibiotics to animals and to humans. And we need responsible, therefore, prescription in those sectors, because when we do that, then it's possible that we prevent the pollution of the environment with antimicrobial resistant bacteria and antimicrobial resistant genes. And hence, we will be able to fit in that missing puzzle. Because once that puzzle still remains away, then no matter how much we fight, for those who understand community acquired infection, they will understand that a lot of people come from their communities with infections already resistant. And most of them come from communities that do not have drinking water, communities that do not have clean sanitation. Therefore, the environment is playing a very big role. So controlling the human and animal use of antimicrobials will help us control that use in the environment. And therefore, filling that puzzle and sealing the One Health sectors. Thank you very much for your kind attention. Talking about prescription, you will see from my picture that somebody says he needs antibiotics because he has a cold. Thank goodness there was our guy there to tell him that, look, it's caused by a virus, you don't need antibiotics. In developing countries, we have antibiotics for even flu infections, which is not the right thing. So this awareness, therefore, will be very, very, very necessary if we need to control antimicrobial resistance in the environment. Thank you very much for your kind attention. I'm open for questions.
Thank you so much, Dr. Akebe Luther. That was a well-informative presentation. We really appreciate having you here. I think maybe we can move over to the second presenter, and then we'll take questions after here. I'm not sure if we've managed to get hold of Mtiani. Dr. Mtiani, is Dr. Mtiani here now?
Yes, Dr. Lekota, can you hear me now?
Yes, correct. Okay.
Thank you very much.
We'll hand over to you. Dr. Mtiani is affiliated at the Department of Animal Science, School of Agricultural Science, in the Faculty of Natural and Agricultural Science here at the Northwest-University. Over to you, Dr. Mtiani.
Thank you very much, Chair, and my sincere apologies to you and all the colleagues. I hope you can hear me very well now.
Loud and clear.
Thank you very much. It was apparently technical glitches that didn't allow me in. I could hear you and everything else, but unfortunately from your side, you couldn't hear me. Right, colleagues, the topic of my presentation is mycotoxin potentiation of antibiotic resistance and the ameliorative role of thiol antioxidant compounds, a perspective. Colleagues, this is not a presentation based on my personal research. Instead, it's based on a review of the literature that I've tried to conduct over the past couple of months, and I'm hoping to produce a publication out of this work. And also, I've gotten a PhD student for next year who will be working on this particular aspect. It's a perspective that I would like to share with you as part of the Antimicrobial Awareness Week, because the literature that I've read so far suggests to me that the problem of global warming, which increases the prevalence of the fungi that produce the mycotoxins, may also exacerbate the problem of antibiotic resistance. And this is what I would like us to look to share with you through this presentation, colleagues. Generally, as you would be aware, colleagues, in animal production, we produce a lot of a lot of farm animals such as chickens, for example, pigs and others. And to feed these animals, we tend to use maize as the major ingredient. As you would know, maize is the major ingredient in poultry diets, whether broiler chickens or layer chickens. Also in pigs, we tend to use a lot of maize, especially in sub-Saharan Africa. So I think there is a possibility that the use of maize and other feedstuffs that are contaminated with mycotoxins might contribute to the problem of antibiotic resistance. Colleagues, as you might have seen also in the literature, that some of the major consumers of antibiotics are farm animals, particularly pigs. Pigs are said to be the greatest consumers of antibiotics globally, followed by chickens and as well as cattle. Antibiotics are generally used not only to prevent diseases, but also to fight diseases and also to promote growth and therefore feed conversion efficiency in farm animals. As you would be aware, farmers, they're always pleased when their animals grow quickly and therefore produce the meat or the eggs or whatever products they desire quickly. So antibiotics have been used at subtherapeutic levels in animal diets in order to improve feed conversion efficiency and to promote growth. Unfortunately, there is a lot of evidence in the literature indicating that the consumption of foodstuffs or animal-derived foods from these farm animals may be a conduit or a route through which the antibiotic resistance genes from farm animals are transmitted to human beings and therefore causing this problem of antibiotic resistance in human beings. And I must also point out that the problem of antibiotic resistance is also a serious problem, in farm animals. We are looking at various strategies as animal scientists that can be used either through the diet or through drinking water or through other means of administration in order to improve growth and to fight diseases in farm animals. Now, as you would know, the manure from farm animals is also used as fertilizer. So it is spread into, it gets spread into the environment, and that might end up into the human food chain, and therefore ending up in human consumers and being the conduit for the transmission of these antimicrobial genes, antimicrobial resistance genes to human beings. The slide here shows some of the antibiotics that are commonly used in farm animals, such as the tetracyclines, the tylosins, erythromycins, salinomycins, doxycycline, and others. So these are some of the antibiotics that are commonly used, in pigs, particularly pigs and chickens. Also in cattle, we do use the antibiotics, but pigs and chickens are primary. Those are the two animal species in which antibiotics are primarily used. Colleagues, as I said earlier, the antibiotics in animal production are generally used at subtherapeutic doses or levels in order to enhance growth and feed conversion efficiency. However, it has been found that this practice has inadvertently led to the development of antibiotic resistance. There's a lot of evidence in the literature showing that the misuse as well as the abuse of antibiotics in farm animals has resulted to this problem, which is not only a problem in farm animals, but also in human beings as well. And as a result, this compromises animal health as well as animal productivity. And also it limits the ability of farm animals to produce food that is so desperately needed, particularly in Africa, in order to feed the rapidly growing human populations in the continent. As I said earlier, there is evidence showing that mycotoxins are very much contributing to this phenomenon. Although the evidence is not very extensive currently, but there are some patches and pieces of evidence that I've tried to put together that do suggest that mycotoxins also do contribute to this phenomenon of antimicrobial resistance. Apart from the problem of antimicrobial resistance, colleagues, the mycotoxins in the form of residues in animal products also pose a risk to food security as well as food safety. Also, the dietary consumption of combined or combinations of mycotoxins impairs the ability of farm animals to convert feed into food. And I think that the problem of global warming and climate change is providing conditions that are suitable for the proliferation and growth of these fungi that produce these mycotoxins. There is a lot of evidence in the literature, colleagues, that show that with global warming there is an increase in environmental temperatures, an increase in carbon dioxide concentrations in the environment, and also an increase in drought stress in plants. For example, in the case of maize, there is evidence showing that climate change has not only increased the prevalence of the fungi that produce the mycotoxins, but also climate change has increased the expression of genes that regulate the production of these mycotoxins. So it does seem that as climate change progresses, there is more of these mycotoxins, of these fungi that produce more and more of these mycotoxins that are so much problematic in farm animals that may also be, causative in this problem of antibiotic resistance. I'll show you in some of the slides as to how I think this is happening. Colleagues, as you would be aware, maize is mainly used as a feed for farm animals, but also maize is also a staple food for most of our communities, especially in the African continent. In the case of maize that is rather contaminated with mycotoxins or infested with the fungi, we tend to feed such maize or such grains to farm animals. But we always forget that the residues of these mycotoxins might be transmitted through the animal-derived products such as meat, milk, eggs, and others into human beings, and therefore possibly contributing to this problem of antibiotic resistance in the human population as well. But in terms of farm animals, mycotoxins generally cause poor animal growth performance, poor quality of products such as meat, milk, and eggs. They also induce toxicity. They are teratogenic, carcinogenic, causing cancer, compromising the immune system in farm animals, and also interfering with growth and also causing death in some cases. Some of the mycotoxins that are notorious and that are very much problematic, especially in sub-Saharan Africa, include the aflatoxins, the ochratoxins, the zearalenone, T2 toxin, HT toxin, DON, and others. Colleagues, as I said earlier, mycotoxins cause a lot of deleterious effects in farm animals. And these deleterious effects include the depression or the perturbations in terms of growth of embryos and fetuses, also perturbations in the histology of essential organs such as the liver. For example, if you look at the image at the bottom left side of the slide, you can see that even the color of the liver changes significantly with the increase in the dietary mycotoxin concentration in these animals. Also, as you can see in the images of the chickens, these are some of the deleterious effects of the mycotoxins. In particular, the aflatoxins, they are very notorious for impairing growth, in the chickens. And the question is, how does this happen? Colleagues, you will be aware that the major hallmark of the toxicity of mycotoxins is the induction of oxidative stress, which is characterized by the supraoptimal production of free radicals and reactive oxygen species, in contrast to a decrease in the antioxidant systems like glutathione, vitamin C, and many others, including the antioxidant enzymes such as catalase, superoxide dismutase, and many others, which are depressed during oxidative stress. And as a result, there's a cascade of signaling mechanisms that usually occurs as a result of the toxicity of mycotoxins. Colleagues, as I said earlier, there is some preliminary evidence that suggests that the mycotoxins through the diet, so administered to farm animals through the diet, may interfere with the efficacy of antibiotics. In this regard, there is a study by Goossens and others in 2012, and also DeMille et al. In 2015, where they have demonstrated that pigs that were fed diets contaminated with with mycotoxins. I think they tested T2 toxin as well as DON in this particular study. No, these animals had low plasma levels of antibiotics, and that suggests that the antibiotics, sorry, the mycotoxins, in particular the T2 toxin as well as the DON or the deoxynivalenol, they interfere with the bioavailability or the absorption of these antibiotics into the systemic circulation of the animal. However, the same researchers demonstrated that in contrast, in the diets where they had included the mycotoxin binder, there was an elevation in the plasma concentrations of the antibiotics. For your information, colleagues, the mycotoxin binders, they include the clays or the bentonides and the vermiculites and other feed additives that are ordinarily included in animal diets and sometimes in drinking water in order to bind or sequester or to complex the mycotoxins so that they do not cause toxicity to the animal. So in this particular study, they included a clay product as a feed additive. And as you can see in the graphs here, in the diets or in the animals that were fed diets with the mycotoxin binder, there were higher levels of the antibiotics in the plasma. So that indicates that the mycotoxins interfere with the absorption of these antibiotics from the gut of the animal. And in contrast, if you include a mycotoxin binder that binds the mycotoxins and therefore inactivates it or prevents its absorption, you are able to increase the plasma concentrations of these antibiotics. So in this case, they tested 2 antibiotics, which are doxycycline as well as paromomycin. The question is, how does this happen? How do mycotoxins interfere with the efficacy of antibiotics? Colleagues, my thinking or the literature that I've read through suggests to me that since mycotoxins have antimicrobial effects by their nature, they would therefore interfere with the gut microbiota. And by so doing, they will alter the production of metabolites, including the antioxidants, like the thiol antioxidants that are so important to quench the oxidative stress that is induced by the mycotoxins. There are a couple of studies that I've looked at, for example, by Young et al. 2020 and others, where they used broiler chickens, and they demonstrated that the dietary administration of ochratoxin A, which is one of the mycotoxins, was able to decrease not only the richness, but also the diversity of the microbiota in the cecum. Also, Wang and others.
Sorry to interrupt you. Just kindly note that you're left with only 3 minutes to wrap up.
All right, thank you. Let me try to finish. Yeah, so there are other studies that have shown in ducklings, that the mycotoxins are able to change, the abundance as well as the diversity of the gut microbiota. These are some of the studies that I've looked at that suggest that the mycotoxins are able to alter the profile as well as the abundance of the gut microbiota and therefore induce oxidative stress. And how does this happen? Colleagues, the literature suggests that the gut microbiota actually play a very significant role in the production of thiol compounds, which have antioxidant effects. And that means that if the mycotoxins interfere with this gut, with the gut microbiota, they will inevitably interfere with the production of the thiol compounds and therefore lead to the induction of oxidative stress. There are many studies that have shown that the gut microbiota are important for the production of thiol compounds. For example, the studies that I've tried to show in this slide. Colleagues, there is also literature showing that the thiol compounds are important, to potentiate the efficacy of antibiotics. So there are many thiol compounds that have been tested and demonstrated to potentiate the efficacy of antibiotics, such as thiomandelic acids, captopril, N-acetylcysteine, which is a commonly used drug, and many others. These are some of the studies that have been used in this regard to show that thiols are important for the efficacy of antibiotics. This is another slide showing some of the studies that demonstrate the efficacy of these thiol compounds to potentiate antibiotic efficacy. Colleagues, let me not bother you very much with the mechanisms as to how antibiotics, interfere. Right, this is some of the literature that I have read through, and I must thank you very much. As I said, colleagues, this is a perspective, and I'm hoping to get collaborators, people that I can work with, as part of this project, particularly people with expertise, in microbiology to look at the gut microbiota, and also people with expertise in antibiotics, so that we can look at how thiol compounds can be used to modulate the efficacy of antibiotics in mycotoxin-infested farm animals. Thank you very much.
Thank you so much. Thank you, Dr. Mtiani, for the lovely presentation. I think now we'll just directly jump over to questions. I think most of the presenters already attended some session where we already asked some of the questions. So I see on the chat there is a question, I think it's directed to Dr. Luther, if I'm not mistaken. There's who's this? There's physician Celestino is asking what are the risk factors for the dissemination of resistance from livestock to the population, and how the resistant gene is transmitted, and what are the recommendations to limit the resistance in farms and its dissemination?
Hi, Doug, is the question directed to me?
I think it's directed to Luther. Dr. Luther.
Okay. All right.
So,
yeah.
But I think both of you, anyway, you can, because this is about what are also the recommendations that could also.
All right. No, let me allow the other colleague to go first.
Yeah.
Okay, I will start with the recommendations already. I think that we have a list of critically important antibiotics which the WHO has put forward. And while we can control that in big farms, we still neglect like backdoor farming, backyard farming in local communities where antimicrobial purchase is unregulated. So these people have access to antibiotics which they use even though they were not supposed to use in animals. So that already needs to be taken out. Within South Africa, for example, there is also a gradual move to improve biosecurity within animal farming, such that they will limit the use of antibiotics, except in the case of direct illness to the animal. So they are moving away from I've forgotten that name, that mass treatments of everything, whereby the antibiotics are just added as supplements into the feed, added into their water and everything. So that I am starting from the solution part. If we improve biosecurity, if we reduce intensive farming, because that's another thing, the push and the demand for more meat and more animal products is the reason why we have the the high production and the need for intensive farming within closed areas. And those closed areas, therefore, lead to greater chances of the animals getting sick. And when they have these greater chances of getting sick, then the need for antibiotics. So if we kind of adopt a more open environment, animal farming, reduce intensive farming, then we reduce the antibiotic use. If we improve biosecurity, I'm not a veterinarian, but I think I've heard them speaking a lot about it. If we improve biosecurity, then we reduce. Now, looking at the transmission from animals to humans, it is multifaceted. First of all, we have the direct transmission, like the direct transmission where based on our feeding habits, I don't know whether there are some, but based on our feeding habits, there's a lot of things now, like where water is used, for example, for irrigation. There's a lot of studies that have shown that antimicrobial, antibacterial, antibiotic-resistant bacteria have been isolated from vegetables, for example, like lettuce and spinach. So those are already modes of transmission. We also have poorly cooked food.
Thank you, Dr. Luther. I think you've said a mouthful.
Okay.
Maybe we could now maybe just attend that. How do the resistant gene is transmitted?
Okay. The resistant genes are transmitted. There are different ways of transmission. Within the environment, there are different mechanisms of being transmitted. Either bacteria that die and release their resistant genes, which become like free DNA within the environment. The other bacteria or related species can pick that up. The mechanism of gene transmission, of resistant gene transmission, is not different from any other DNA transmission. So they will either have, just by transformation, picking free DNA in the environment, which they incorporate in their system, or we will have the transmission, which will be through viruses in the environment, like the phages when they attack. That will be through transduction. And we have the conjugation process that has been shown to transmit these genes between bacteria, related species, and even unrelated species. And when humans are exposed to that environment, then they also get that back into their systems.
I think it's well said. Thank you so much, Dr. Luther. I hope all the questions are answered. I think there was a clear clarification on that. So I think now we could actually, if there's no more other questions, I think we are running out of time. We're gonna have to end the session. Before doing that, handing over to the vote of thanks, just kindly note that we request all the students, all the participants that are in this webinar to make sure that the videos is on so that we can just take a screenshot as a show of appreciation that you actually attended this webinar. So that will be after the vote of thanks. So for the vote of thanks, we'd like now to hand over to Professor Babalola to give the vote of thanks. Over to you, Professor Babalola.
Yeah, thank you so very much. I first would like to start by appreciating our coordinators in the person of Dr. Lekota and Professor Rashid. You have done wonderfully well. Thank you so much, because this topic is so needed at this time. And I can see you also agree with me, the enthusiasm with which the presenter spoke. Thank you for coordinating. I want to say a very big thank you to our Dean, our amiable Dean, for the opening. Prof, that was beautiful. Thank you. And ladies and gentlemen, this Happy Thursday is a great one. And it also gives me immense pleasure to say a very big thank you to the local organizing committee in the person of Professor Ateba, Dr. Molale Tom, and Professor Bezende. You have done wonderfully well. Thank you for keeping the flag flying. And I'm sure that so much that has been learned today that even the presenters and all in the audience appreciate the local organizing committee. And I must say thank you again to the presenters. We know that this is a much needed topic, and these scientists have spoken so well, both the fully grown one and the upcoming one. Thank you, Professor Mwanza, Mr. Tuto, Mr. Jacobus, Dr. Gerald, Professor Shigo,
Dr. Emilia, Mr. Daniel, Mr. Chris, Dr. Mitiani, Ms. Bukola, and Dr. Habia. We just want to say you have done wonderfully well. And I'm glad that this virtual presentation, because we are going to be referring to it even long after today. Thank you so very much. See you some other time. Thank you.
Thank you so much. We would like now to we would like to so that all the students and all the participants to open up their videos so that we can able to take a screenshot. Can you show up your videos, everybody?